design patterns. So we can say that we can broadly categorize all the design patterns into four basic broad divisions. The first is creational design patterns, how the objects are created, behavioral design patterns, structural design patterns, and J2W design patterns. I'll be focusing on this particular part in this particular video, and if you want me to cover all the three remaining parts, please let me know in the comment section. Then only I'll be creating videos on the three parts of design patterns. Currently, we will be focusing on creational design patterns. So let's get started with them. So before we get started with the creational design pattern, the next very important interview question may arise before going into deeper into those particular things is, why do you actually need design patterns? So we know that we can find a solution to any of the solutions by our own. We are great enough for that. But why do we need these design patterns? So first of all, I want that the solution have the singleton design pattern, then everybody will have the design pattern of singleton type, as in a single object being shared among various applications. The second reason why we need design pattern is that these design patterns are actually nothing but a tried and tested solutions to some common problems. Thus, it reduces the technical risk. If I come up with my own solution, there might be some technical risk, and the project may have to deploy a new and untested design. To prevent this, I'm going to use the design patterns which are actually tried, tested, documented, and they are very common to those problems. Thus, it saves your time and effort during the development stage or the implementation stage of software development lifecycle, SDLC. The third important reason is that they are language neutral. It's common to all the languages which supports object oriented, though it is C++ or Java or any object oriented languages. And since it is well understood and documented, the final product, that is whatever I'm going to create as a Java application, has my your Java. For example, this I'm a better understanding of it. So what this snippet for this design, this particular design pattern, factory design pattern. So I have created this particular thing for you. So I have told you that we have, suppose I have a particular profession which is my interface. My profession can be of three different types. I can be an engineer, I can be a doctor, I can be a teacher. So how I am going to denote this in my programmatical way? So profession will be an interface, and I have a particular method, say print, which will print what I am actually. Then I'll be implementing this interface in my different concrete classes, say doctor. So doctor will print, I'm in doctor class, engineer will print, I'm in an engineer class, and teacher will print, I am in the print class of print method of teacher class. So this is how you implement your interface with the different concrete classes. Now, what factory pattern says that I want to create an object of doctor or engineer or teacher, but I don't want to show you how am I creating that object. So what you have to do, you have to create a factory for it, as the name suggests. So what does this factory class do? This factory class does nothing but takes a type what you want to have. Say I want to have a doctor. So if you say doctor, it will give you a new doctor. If you say engineer, it will return you a new engineer. If you say teacher, it will return you a new teacher. So suppose this is my main class, or what you can
Stop. What is the fastest way to learn generative AI? Well, use generative AI.
Hey guys, welcome to Code Decode. Services, how will they actually communicate with each other? What are the ways in which you can make them communicate with each other based on your business requirement? Then what is the difference between monolithic architecture, SOA architecture, that is service oriented architecture, or the microservice architecture? What are the difference between all the three? Then most of the companies, what is happening nowadays is they are having monolithic application. Now you being a developer, you are asked to design and modify the monolithic architecture to microservice architecture. If you are asked to do so, it's not that easy. So what are the best practices you should remember, and how you should do that is what we are going to also cover in this video. Then which database does microservice based architecture prefer? So there are multiple databases out there in market. So which database will you prefer for your microservice architecture is the most asked questions nowadays in an interview. Then what are the important design patterns that you have used while creating a microservice architecture is also one of them. Then we are going to cover what are bounded contexts. Then when you are all done with your creating your microservices and interacting them with each other, the last thing that you need to do after designing everything is how will you test your microservices that you have created. Then with all these things done, don't you need to secure your microservices? So you need, how you monitor your microservices? What are the tools out there in the world for microservices? I'm planning to cover in this series. If you need to add something, remove something, or manipulate something here and there, you have to let me know in the comment section. Just make sure that this is an interview series, so I'm not going to create a tutorial on each of these topics. I'm going to touch each and every topic so that you are capable enough to answer these questions in an interview. If you want tutorial, we have already created before creating this series. It was pre-decided. So if you go to the Code Decode channel, the playlist, you can see there's a playlist here called microservice tutorials. We have 5 tutorials created for you here. Here we have created a basic video which explains everything about microservice. Then how would you implement microservices using Eureka? Then the fault tolerance mechanism, the design principle called as fault tolerance, then a design principle called API gateway. What is it and how to implement it in Java code? Everything is everything and anything is explained here end to end in these videos, which is a tutorial. In these questions, I'm going to cover just the interview perspective part. If you want us to cover the tutorial, or if you want that we should take one of the topic out here and create a tutorial on that, you have to let us know that particular topic in the comment section. Then only we are going to do that. So let's get started now. What are microservices? So microservices is nothing but an architecture. So we have seen many kind of architectures, right? MVC architecture, many kinds of architecture we have seen. So microservice is also an architecture where application is exposed as loosely coupled services that can be independently developed, deployed and maintained. Too much of theory. We have already covered this. What UI, what citizens can do is register themselves with an OTP coming on their mobile number, right? So citizens can register themselves and they can also see which vaccination center is available and book their slots. So what we have done in our implementation is we have created two services, vaccination center service and citizen service. Both of these services are loosely coupled because they are independent services here. They are independently developed. They can independently be deployed because this is a Spring Boot application. They have their internal Tomcat embedded into itself. So the two servers are also different. That is why they can be independently deployed and hence their port numbers were different. One was 8081, one was 8082. So they are independently deployable and maintainable also. If something went wrong while a citizen is trying to add itself to the UI portal, that means there is some issue in the citizen service and not in vaccination center service at all. Then we just have to maintain and troubleshoot the issue in citizen service and nowhere else. That is why they are independently maintained. So each service is referred to as a microservice. So this is our citizen microservice and this is vaccination center microservice. And each service performs a unique function. What is so good about this microservice architecture? So the specialty of this architecture, it is polyglot. And what does that mean? If I have a team which is working on a microservice using Spring Boot, Java, MySQL, there can be another team who can develop another microservice. So the one who is developing Java, Spring Boot, MySQL is suppose vaccination center service. doesn't mean my citizen service also has to have the same kind of technology in their tech stack, that is Java, Spring Boot, MySQL. Another team can actually work using Python, Node.js, NoSQL. So in today's market, where the market is such a volatile one, it's very difficult to get a team of 5 to 6 people working on the same technology. So this is why most of the companies are actually moving towards microservice architecture, because even people with a different tech stack can work together in one single application. So what is the advantage? The advantage is different microservice can use different version of same programming language. So it can be a case my citizen service works upon Java 11, my vaccination service is still on Java 8 due to some reason. So this is also possible. It's completely fine. The second thing is microservices can use different programming language also. I have already told you my one team who is working on citizen service is on Java, Spring Boot, MySQL. My another team working on vaccination center can be on Python, Node.js, NoSQL. A completely different language, not connected to each other in any ways. Similarly, different microservices can also use different architectures as well. That is all about what are microservices. We will move towards why microservices now. So in case of monolithic applications, there were several problems. So first of all, what were monolithic applications? If I would have created this whole application as a monolithic application, there you won't be able to see different CPUs or so the advantages is you are able to use different kind of technologies. So I have make your changes and deploy the whole application, which actually includes citizens functionalities also. But in the case of microservice, you don't have to do that. Just the vaccination service will be capable enough to be deployed alone with version 1.1 and citizen can remain on 1.0, and hence individual deployable units are allowed in microservice architecture. Then it also allows frequent software releases. As soon as you make some changes, you can deploy it. You don't have to wait for citizen service to make their changes and deploy it. Ensure security at each service. Here in monolithic architecture, you have to have one way in which you can have the security implemented. In this case, in each of the microservice, you can implement your own security in your own way. So you have even a free hand in implementing the type of security you want to implement in each of these services. One can have Okta, one can have Auth 2, it's completely fine. Multiple services are parallelly developed and deployed. So I've already told you, I had a team of 5 people here, I had a team of 5 people here, rather than 5 people just working on both of them. So the development task will be completed twice as faster as this one, and hence your time to market will be reduced. Now, what are the disadvantages? If it is so good, if it looks so good, there must be some overhead of using microservice architecture. Yes, there are many overheads of using microservice architecture. So what is it? Currently, you just have few number of microservice here. I just had a vaccination center and a citizen center. What if my business domain starts growing? Then your microservices also starts growing in number, and managing those n number of microservices is a difficult task. Now, communicating between microservices is a complex thing. Why is it so complex? We have done this already using the REST APIs. It was so quick. We just hit vaccination center once and we just not get the data of vaccination center. We also get all the citizens who have registered to this vaccination center. Now when a business expands, now suppose there is one logging microservice which is separated from all the microservices. Now when a hit comes to microservice 1, say suppose vaccination center, you can give a call to microservice 2, which is citizen service, no problem, and then you can respond back. But in the meantime, I also want to log each and every request going and coming. So suppose I have a third microservice doing that, but these are independent of the client. So client does not need to wait until you log your things, right? So what you can do is you can make it asynchronous. You can put your data on an active MQ and you can leave it. So whenever your logging microservice is up again, it don't have to wait for its task completion. What it can do is it can pull your request from this queue and it can respond back to you. So this is asynchronous communication. We are going to cover that in few seconds. But these are the chances that handling microservices with different business requirement is a tough task. Third point, increased efforts for configuration and other operations. So here you can see in a monolithic one, what would have been done is one single application is created. It is capable enough to handle everything. Now in microservice, just for creating citizen and vaccination, we also needed one Eureka server, one API gateway, and many more things. So just for creating one application, you had to create 4 different Spring Boot applications and configure each of them with their application.yaml files or application.properties file. So this was so much of configuration you had to do. So that is one of the cons of microservice architecture. Fourth thing is it is difficult to maintain transaction safety and data boundaries. So now your data can move between one microservice to second to third to fourth. It's very difficult to maintain the microservice transactions, and hence we also have few design patterns to do that, but yeah, it's a difficult task. Now, due to decentralized nature of microservices, more and more microservices will mean more resources and hence high investment. So it looks like, okay, it's so good that our one team is working here, one team is working here, but if you can see, the number of people working also increased. So where I had a billing of 5 people for client, now I need 10 people's billing for client, and hence it is high investment. Where I needed just one server, now I need 2 servers to be able to deploy my different microservices. Now if I had n microservices, I might have needed n servers, and hence high investment. Debugging is a problem because now your data goes from one microservice to different, where if suppose your data got lost in third microservice, how would you able to debug it? It's very difficult task. So debugging is a problem for sure, but if you use the right instruments, like I'm going to tell you in few minutes, then it's easy to debug your issues. Now microservice will need a large team size with the right mix of experience on design, development, automation, deployments, tools and testings. So why is that so? So I've already told you that we need one team for things. So why is that so? So I've already told you that we need one team for vaccination center, one team for citizen service microservice. Now each of these teams should have one person who can design your database, one who can design your architect your application, one person who is capable enough to do development, one person who is capable enough to do unit testing, integration testing, manual testing, automation testing, everything. So what person you need here is the same replica you need here also. So again you will need everything in double or 3 times. So this also increases the investment cost for you. Now there are so many kinds of disadvantages and advantages. How will I decide when to use microservice and when not to? So when you have a very time crunch, your client is sitting on your head that give this particular application to me within a shorter span of time, then that is the time when you should use microservice, though it will increase your input and increase your team size, but it will for sure reduce your time to market or time to go live. When you need a scalable software, it is always, when will you be able to have the scalability? When you are on cloud. So what particular architecture is cloud enabled? That is microservice architecture. So you should go to microservices architecture when you need too much of scalability. So when number of hits are reduced, you should have less number of servers with you. When a very large amount or bulk amount of people are hitting your application, you should have more servers in place. Then you go for microservice architecture. Only in cloud you are able to do that. Also when you want to lower the cost, now you'll ask me, there are n of 5 people here, 5 people here rather than. So when you want to lower the cost, now you'll ask me, there are n of 5 people here, 5 people here rather than 5 only, then how are you reducing the cost? So when you use microservice architecture, you make your application capable enough to be deployed on cloud. Now on cloud, what happens is, when initially few vaccinations were to be registered, so we had suppose 50 people registering every day. It can be handled just by one server. Now when cases started increasing, 50,000 people started registering to our particular application. For handling this, you at least need 5 to 6 servers. Now if you would have made it a monolithic application, in this particular second scenario, your application would have been down if just one server was there. To analyze this issue, and if you have application to cloud, or your cost. So you are just looking at a very small for you, which makes your life much more easier. Simple application who just, like for example, this is a real-time example I can give you in my real life. There was an application which was developed and maintained in Excel sheet. What one person has to do is go and add data in Excel sheet, calculate addition, calculate multiplication, various formulas, everything he has to do on its own. Now this can be automated. So what you can do is, you can just create a simple application to automate this thing and convert it into application who takes the data, convert and applies the formula and gives you the result to the client on the front end. So this is a simple application. You just need to convert an Excel sheet data into an automated application. So this is a simple part. So you can use monolithic application here. You don't have to go for microservice architecture. It will give you load on your investment part. So you should first ask yourself, do you really need microservice architecture? Because it comes with a cost. So if it really needs that, you have a business need that you have to decouple your services, go for it. That's when you should use the microservice architecture. Now, how does microservice architecture works? We have to cover so many things, the features of microservices, how do they communicate with each other, difference between microservice, which database to be used, multi-database model, which one, what are the, so I have so much things to cover, like how to deploy in Docker, how to deploy in AWS, many more things to cover, but I cannot do this in this video. If you want us to create the second part or third part of this video, just let us know in the comment section. We'll create the second part of it. And we have a like target of 300 likes. Once we cover the 300 like target, we'll put the second video on the scene. Thank you.
Hiring for AI and ML roles has been increasing by 30% each year after the pandemic, while demand for other tech roles has only grown by half the rate. Due to the rising demand and the lack of skilled professionals, many companies are increasing the pay for these roles. So, if you're interested in machine learning, now is the right time to make a shift. And to help you understand what steps you need to take to make that happen, we have a masterclass on Roadmap to Become a Machine Learning Engineer. Go from understanding.
Hey guys, welcome to Code Decode. This is the second services. Like for example, this is our Citizen microservice. This is our Vex. There is no way to do that because the port numbers on which these instances are running on cloud is completely dynamic in nature. So to prevent that particular scenario that you are not able to discover this particular microservice, there is discovery service. And here in case it is Eureka for us. So it is a registry. It says, okay, currently my microservice 1 is working on 8081, microservice 2 is working on 8082, and 3 is working on 8083 and so on. As soon as your instance gets changed with the new IP address and port number, this particular registry crosses this particular one and updates it to 808485 whatsoever new port number it has got or the new IP address it has got. And hence whenever this particular microservice wants to go to microservice 3, it asks Eureka, where is microservice 3? It says okay, it was on 8083 but the updated one is 8084, so I'll give you an address of 8084 and there you can find microservice 3. So that is why Eureka was that important in our architecture. So whenever it comes to microservices, the very important part is the discovery service, which helps you to discover microservice so that you don't have to hard code its URL and port numbers in the application itself. The second important part was API gateway. We have covered why was it important. It actually does many kind of functionality that you don't have to implement the security and everything here. You can do everything at this one platform. It is an entry point because your front end should not know which URL, which port number your microservice is working. It should just know one application which interacts with, and the task of API gateway is to route based upon your requirement. So this is the architecture and how it used to work. We have already covered these important things in the tutorial. Link for the playlist is given in the description below. Now, what is the main feature of microservices? So there are multiple features because of which microservice got so famous in the market today. The first very important one is that it breaks the application into smaller services. Because of this, it is possible to deploy and develop each of these services independently, and hence new feature introduction becomes very much easier. So there can be a case that one of my application, Citizen service, is working on Java 8, but my team working on vaccination center is much more fast forward. It wants to do much more enhancements and it just moved to Java 11, and still both are interacting with each other comfortably. So that is why introduction to new features is very much easier. Second point is decentralization is involved in microservice architecture. So what does that mean? So it means that your data management is decentralized. There can be a monolithic database which is common to all the service, or there can be one database for each microservice depending upon your business. But the point is each service has an ownership of data related to business functionality of that service. So every microservice is going to fetch only the required data from database and rest is removed. So that is why decentralization is what is introduced with microservice and hence the loose coupling. The third very important feature is black box. What does that mean? It means that my vaccination center does not need to worry about any of the citizen service business logics or any of those things. It is completely black box. The citizen service is completely black boxed to vaccination center. What does that mean? My vaccination center does not know anything about citizen service. What technology it is using, whether it is using Java. So I am on Java. Is citizen service also on Java? It doesn't need to know. It does not want to know. It does not need to know. Because it can be on any of the technologies it wants to, and hence the complexity is hidden from the other services and components, and hence it is black box in nature. The fourth important feature of microservice is security. Now, microservice platform itself provides some capability for certificate management, different types of credential, authentication, authorization, authentication based on role-based access models. Everything is provided by microservice architecture. But a very important feature here is security is decoupled from microservice development team as it is platform standardization. So the task of implementing security is now given to API gateway. You can implement the security on this level and your developers need not worry about the security at all. The person developing and handling the API gateways and the platform will be capable enough to do that for you. So that is why even the team working for the different microservices need not worry about security.
विवेक आप गए नहीं?
सर वो
बेटी का टूर्नामेंट था ना आज?
मीटिंग है सर.
अब जाओ. जाओ. फोटो जरूर खींचना.
If you allow us, we'd love to.
Chai, garma garam chai for everyone. Whiskey on the rocks, right?
No, too early. Let's go. That's got it for you.
यार परसों इस गधे का फेयरवेल है. मैं सबको ग्रुप पे मैसेज डाल देती हूँ.
ऐसे बुलाएगी सबको? रोया हमेशा के लिए लंदन जा रहा है. पता नहीं यार फिर कब मिलेंगे. तो जो भी करते हैं दिल से करते हैं, है ना?
जब साथ है डरने की क्या बात है. रोशनी से भरी ये सांस है. मस्ती है और मजाक है. खबरू जज्बात है. बेहतरीन सा ये एहसास है. के प्यारे 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 सारे सारे लम्हात में चला खुद से ही हूँ करने मुलाकात में. जिंदगी तू खास है. तेरे जैसी कोई नहीं है. जिंदगी तू खास
है. Just give me a second, please.
Saturday night meeting.
Saturday, I can't.
I need you, bro.
Saturday. Let's go.
Perfect.
Meet the new one.
No. Yep.
Yeah. Let's go. Let's go.
और भाई लंदन फुटबॉल के 2 VIP टिकट्स बनते हैं.
VIP टिकट्स. हलवा है क्या?
Guys, So as we all know कि गौरव हमारे ऑफिस का चैंपियन है ऑफ प्रेजेंटेशंस, तो हमने भी एक छोटी सी कोशिश की है गौरव के लिए एक प्रेजेंटेशन बनाने की.
The very important destination center, message 3, when the logging service is done with message 1, it will pick your message 2 from queue and it will log into its logger. So this is asynchronous nature and this is synchronous nature. Waiting for the response and again giving back response to UI is a synchronous one, but you are not waiting for response and you are logging and you are putting message onto the queue, and forget about it. Logger service will automatically pull your data from the queue, log it into its logger, and it doesn't want your response back. Till then, when you get back and saying that I'm done, all the 3 messages are logged into your logger, by that time your user have been taken its response long back. So that is asynchronous nature. So now let's get back to the theory. There are 2 types of inter-service communication we have seen, synchronous and asynchronous. In case of synchronous communication, client waits for the response within a time limit. The possible solution is using HTTP protocol via REST API for inter-service communication. We have seen this, we have implemented all these applications using synchronous nature REST API. The second one is asynchronous communication. In case of asynchronous communication, client doesn't wait for response from another service. What it does is, when the client microservice call another microservice, the thread is not blocked till a response comes to server. The message producer service generates a message and sends it to the broker on a defined topic. Too much theory? So this is called, the queue that I've created is called a topic. This is a message producer. It produces a message, put it on a queue or the topic, and then message producer waits for only the acknowledgement for broker to know message is received by the broker. So only the time till this broker or the topic says, yes, I have received your message, till then it waits, and then again it starts publishing another message to the broker. So it keeps on producing message on the broker until it has been done with its work, and it waits only for the response from broker and not from the logging service. The consuming service, here in our case it's logging service, is the consumer service. Subscribe to this topic in the queue. All the message belonging to the topic will be fed to the consuming system. So all the message which comes here is given one by one to this service to log. The message producer service and consumer service doesn't even know about each other. So logging service doesn't know about vaccination center doesn't know about logging service. They interact with something called as intermediate one, which is the broker or the topic in our case. The response is received in the same methodology through the message broker via defined message topic. So the same thing happens. It gives there must be some consumer here. It gets the message, logs it and sends response. Okay, I got it. Give me the next one. It logs it. Give me the next one. So this is completely asynchronous in nature. They doesn't communicate directly with each other like vaccination and citizen service in our case. So what are the tools out there in market for this type of asynchronous communication? The tools are Apache Kafka, RabbitMQs, ActiveMQs, and these are based upon advanced message queuing protocol system. The video on tutorial on this topic is not yet created. If you want to have a look at how ActiveMQs and RabbitMQs work, how Kafka work, the detailed demonstration with Java based application, if you want that, just let me know in the comment section. I'll create that one for you. Now, what is the difference between monolithic architecture, service oriented architecture and microservice architecture? A very important question from interview perspective. So now I'll give you an example first and then we will go into the depth of this. So I go to an interview asks you, how did you implement your microservice? I say, I have one vaccination center, I have one citizen service center, and they both interact with each other through REST API, and that is my microservice architecture. Then and there your interview will reject you. Why? Because what you have answered is that you have one application, you have another application, they are interacting with REST API. This is not microservice architecture. This is service oriented architecture. So you should for sure clearly know the difference between what is monolithic architecture, what is service oriented based architecture, and what is microservice architecture. Now I'll give you an example. Suppose I had a citizen service and a vaccination service. They are working on their own. Now there is one Google API. This API takes longitude and latitude, and country city pin is what it returns you back with the directions also in map. So it takes input as this and gives output as this. Now my user, while registering, I ask the person, where do you live? Now suppose I get the longitude latitude from the map and give it to Google API, it returns me with this country, city, pin, everything of that user. So this is an automation. I don't want user to fill a big form which says what is your name, what is your country, what is your city, what is your pin. You don't need to do that. Just mark where you live in your map and I will fetch all this thing. Similarly, while registering a vaccination center to a database, say I want to register this particular school as a vaccination center, then also you just have to give the name and the location. I will fetch latitude, longitude, and I will give all these data, where, in which country, which city, what is the pin of that vaccination center. So these two have a common feature, that is they want these data in their application. Then they both give a call to this API. It gives the directions in map. It gets all the information about that particular location. So this is the service oriented architecture. This is reusing. This is sharing of data. They don't want to implement this API calls independently in their application, and hence they created another API which gives a call to this API. They are just reusing or sharing this data amongst each other. So this is service oriented architecture. But what is microservice architecture? Creating those services separately, creating microservice citizen, microservice vaccination center who doesn't share any kind of data with each other. They are completely independent. They don't share anything. There is no reusability of code. Even though it has some piece of code, it also has some piece of code, but they are not sharing with each other. This is microservice architecture. So very important difference between service oriented architecture and microservice architecture is the reusability of data, and sharing of data is a complete no in microservice and is always agreed upon in service oriented architecture. So let's get into the details of it now. The one monolithic, we have already covered it many times. It is similar to a big container where all your components live and assemble together and completely tightly packed, and hence very high coupling and low cohesion, which is a very bad practice. Nowadays, most of the people with a complex architecture are now moving from monolithic one to microservice one. Service oriented architecture is a collection of services which communicate with each other, and they involve simple data passing or could involve two or more services coordinating with each other. Too much of theory, I've already made you understand what is service oriented architecture. Collection of services which communicate with each other for a common data, sharing of data, reusing of same kind of data. That is service oriented architecture. In terms of microservice architecture, it is a collection of small autonomous services modeled around a business domain. So my business domain says there's a citizen, there should be a vaccination center, then they are completely decoupled. There's a loose coupling, high cohesion, and a very good design practice. So the main difference between microservice architecture and SOA is the sharing of data and information is the main difference. SOA shares and reuses as much as possible, while in microservice we focus on sharing as little as possible. Now we have many more things to cover, but we will be covering these part in the next video. We are also putting a like ratio of 300. If we cross this 300 like target, we will be creating more such content on how to design a microservice, which database to use, what are the design patterns which we use, how to secure it, how to deploy on AWS, Docker, and everything. So let's meet in the third part. Thank you.
खुद का किराया ऑफर करो या ड्राइवर का वो ऑफर चुनो जो आपको पसंद आए। अब ऐप की नहीं, आपकी चलेगी।
Hi guys, welcome to Code Decode. Today in this video, we are going to cover some more important microservices interview questions.
Please like, share and subscribe to support us, and we are setting a like target of 500 likes.
Today we will be focusing on ways to communicate between different microservices. So if you have 2 or 3 multiple microservices and they want to communicate with each other, how many ways do we have so that they can communicate? The very first method is through synchronous communication. Now we are not going to get into much deeper into this type of communication because we have already seen the REST APIs, which was the synchronous communication for us. Here, suppose we have two microservices, microservice 1 and microservice 2. Now microservice 1 wants some data from microservice 2, then it will send a request to microservice 2. Microservice 2 will process the request and sends back the response to microservice 1. Microservice 1 will wait for this response, and this is a synchronous communication. Example of this is already we have seen, that is REST APIs. The second example of synchronous communication is through GraphQL. The third is through Fake Client using Eureka Discoveries, and the fourth is gRPC. Now, in our IT life, we must have used at least two of these synchronous communications, where gRPC is the most common one nowadays, because gRPC has proven itself 10 times faster than the REST APIs. It is developed by Google and is a substitute for REST with many more new features. So if you want to know more about the gRPC and how to implement in your project and what are pros and cons, you have to let me know in the comment section so that I'll create a video on gRPC. Or if you want to know more about GraphQL also, you can let me know in the comment section. Now, in a synchronous call, the service waits for the response after performing a request. So here, our service used to wait for the response after sending the request. Today, we will focus more upon the asynchronous communication because this is the untouched part in microservices right now. And this is the most commonly asked questions in interviews because this increases the performance of a system a lot. So this communication usually involves some kind of messaging systems like RabbitMQs, ActiveMQs, and Kafka. So let's first see what is asynchronous communication. In asynchronous communication, to initiate such type of communication, a microservice who wants to send some data to microservices publishes a message to a separate component known as message broker. So in the asynchronous communication, the major task is done by the message broker, and it is responsible for handling the messages sent by producer, and the message broker guarantees the message delivery. It is a task of message broker to make sure the message reaches to the required microservice. Suppose this microservice 1 is a vaccination center. Vaccination center has some slots available. So there is one more microservice, slots information microservice, who is responsible for maintaining all these slots available for each vaccination center available in the system. So what vaccination center will send it is a slot information, how many slots is available. So it will send the slot information, it will receive the slot information and save it in database, so that next time when a citizen service, microservice 3 citizen service, tries to book a slot, it will ask from the slot information, is there any slot available for vaccination center V1? So it will ask this particular microservice. It will query the database and will return, is it available or not? If it is available, book it, else just try to find another vaccination center. So this type of communication can be done through asynchronous communication also. So what my vaccination center will do is, it will say, I have 18 slots available. It will send this 18 slots availability to this message broker, ActiveMQ, RabbitMQ, or Kafka, and start doing something else. It will start doing its own task for the vaccination center, registration, verification, everything. So it will send the data to this message broker and forgets it. This slot information microservice will fetch this data availability for vaccination center V1 and store it in DB in a asynchronous manner. So basically microservice 1 will not wait for microservice 2 to store the information it has sent, that it has 18 slots available in its database. It will continue its task and it will not wait for response that yes, I have stored your 18 slot availability in my database. It will not wait. It will go on and proceed with the another task. So basically in async communication, a microservice vaccination center will send some data to the slot information microservice through a separate component known as message broker. Message broker is responsible for handling the data sent by vaccination center to slot information center, and message broker will guarantee the message delivery to the slot information service. After the message is received by the broker, so when the message is received by this particular broker, It is now its job to pass the message to the target service, which is the slot information microservice. If the recipient is down at the moment, now what will happen if your slot microservice is down? If it would have been the REST API case, then you will get a 404 not found of 500 internal server. Your application will fail. Your request will fail because it is synchronous. But in the case of async communication, if the microservice 2 is down, then also your task will be done because the broker might be configured to retry as long as the necessary successfully delivery is done. So what message broker will do is it will store this slot information of 18 availability in vaccination center 1 in its own memory and will wait and try until the microservice 2 is up. As soon as microservice 2 is up, it will push the message back to microservice 2. Microservice 2 will get the information, okay, microservice 1 has sent that vaccination center 1 has 18 slots available. It will save it in your database. So this is much more fault resilient and fault tolerant than the REST APIs. Because if this whole communication would have been through REST APIs, if microservice sends one REST API call saying vaccination center 1 has 18 slots and the microservice 2 is down, it will send a response back 500 internal server error or some kind of error that the service is down and your message will be lost. So these messages will be persisted in the message broker and stored in the memory. Whenever microservice 1 is up, it will be successfully delivered. But if the message broker is restarted or message broker is down, then that will be the case when you will lose your data. So there is a chance of fault here also, and that will be the case when your message broker is down. If the message broker is down, then the message which is stored in the memory will be lost. Since the broker is responsible for delivering the message, it's no longer necessary for both the service to be up for successful communication. Now, to ensure the fault tolerance, at least it is not necessary for microservice 1 and microservice 2 to be up all the time and be tightly coupled, because in synchronous communication and REST APIs, if either microservice 1 is down or microservice 2 is down, in both the cases, your message will be lost. So this is tightly coupled. It means that if you want your REST APIs to be successful, it means your two microservices should be tightly coupled and must be up all the time to be communicating with each other. But this is not the case with the async communication. It is the broker who is responsible for delivering the message, and hence none of the services has to be up all the time. Async communication hence mitigates or removes the biggest problem of synchronous communication, that is tight coupling. This async communication makes these two microservices loosely coupled. So the relevant point here is that the sender does not need to wait for the response. So the point here is that microservice 1 will not wait for the response from microservice 2 that yes, I have received your data. Slot information microservice will receive the message in its own time, and the sending microservice, that is vaccination center, is not blocked or logged at all. It simply fires the message that vaccination center 1 has 18 slots and forget about it. The rest of the task will be done by the message broker. Message broker will store it in its own database, and whenever microservice 2 is up and ready to receive the message, it will push that message to microservice 2. Now, a very important thing that we've already seen, this is a fault tolerant communication method. But what if the message broker who is storing your information that 18 slots are available is restarted or is down, and the message stored that 18 slots are available is lost? In that case, message broker is a vital part of asynchronous communication architecture and hence must be fault tolerant. So there are multiple ways to make this also fault tolerant. This can be achieved by setting up multiple additional standby replicas of the broker so that can do failover methods. Since even with auxiliary replicas, failure in the messaging services might happen from time to time. The very first method to make the broker fault tolerant is to have replicas of broker. So you can have multiple broker here, and if this particular broker fails, you can use this particular broker. It will have the replica and copy of the existing broker. Now there are many methods in which this particular message broker can be made fault tolerant. If you want to know more about the fault tolerance of the message broker, let me know in the comment section. I'll move ahead with the type of async communications we have. So commonly there are two types of options in the message-based communication. First is point-to-point and second is publish subscriber. In point-to-point communication, we have queues. In publish subscribers, we have topics. So in point-to-point communication, a queue will be used in this type of communication. The service produces a message. Let's see it through the diagram. So in this type of point-to-point communication, there is only one producer, that is microservice 1, and there is one consumer, that is microservice 2. No multiple publish subscriber things here, just point to point from one to another through a queue. So the service that produces the message, called the producer or the sender, will send the message to the queue in one message broker. So it will send the message to this queue, and the service that has an interest in that message is called the consumer. So this is Microservice 2 is the receiver. In our example, this is vaccination center and this is slot information microservice. So slot information microservice will consume the message from the queue and carry out the further process of the message. Only one message can be sent by the producer, can be consumed by only one receiver, and the message will be deleted after it is consumed. So very important thing to note here is that as soon as your message receives the consumer, the slot information, the message will be deleted from the broker and actually practically in the memory where the broker is storing all its messages. If the receiver or an interested service is down, so if microservice 2 is down, the message will remain persisted in that queue until the receiver is up and consumes the message. So the message will be stored in this message broker until unless message service, the microservice 2, that is slot information microservice, is successfully up and is capable enough to pull the message from the broker. For this reason, message-based communication is one of the best choice for microservice resilience. So this is why we can say that this is much more resilient way than synchronous one. The popular choices for such kind of point-to-point communication is RabbitMQs and AbbitMQs. So ActiveMQs and RabbitMQs are much more efficient in queuing systems with point-to-point communications. The second type of communication is publish-subscriber or synchronous communication. So in publish-subscriber model, the topic is used. The topic in the message broker will be used to store the message sent by publisher, and then subscriber that subscribes to that topic will consume the messages. So this was point-to-point communication. Only one service used to send data to the queue and only one used to take from the queue. But in the publish-subscribe model, there will be multiple microservices who will be subscribing to this topic. And this is not a queue, this is a topic now. There will be one sender, there will be multiple consumers, and all these consumers who are interested in the messages sent by this microservice one will subscribe to the topic.
भैया जल्दी चलो, अब हमारे डांस की बारी है।
अरे बस खा के चलते। एसिडिटी।
इनको कोई जीरा दो
और अजवाइन भी।
काला नमक भी मिला लेना।
इससे अच्छा है नया 3-in-1 वाला इनो पिला देना।
इसमें है तीनों की ताकत जो एसिडिटी से दे जल्द राहत। 3-in-1 वाला इनो, इसमें है तीनों।
Complete your hybrid cloud with HPE GreenLake.
So the topic in the message broker will use to store data sent by the publisher, and then subscribers subscribe to that topic will consume the message. Unlike point-to-point communication, the message will be ready to consume for all subscribers, and the topic can have one or more subscribers. The message remains persisted in the topic until we delete it. So in point-to-point communication, we used to delete the message as soon as the receiver receives it. But in topic, there are multiple receivers. So until we don't go and delete the data in the topic, it is not going to be deleted. In message-based communication, the services that consumes the message, either from the queue or topic, must know the common message structure that is produced or published by the producer. So one disadvantage of message-based communication is that there is one format in which the producer sends the message and the subscriber subscribe to that message. And they both have to come in between and agree to the contract of the format of message-based communication. To mitigate this issue of one knowing the other's message format, there is event-based communications. Now, the example of this publish subscriber is Kafka, a very important messaging system. If you want me to implement Kafka in real times for you, and even if you want me to implement the gRPC or the GraphQL or the other type of synchronous communication methods, you have to let me know in the comment section. I'll create a separate proof of concept or a small demo for you on the same. Now moving ahead to the event-based communication. Unlike message communication systems, we have seen previously the point-to-point and publish subscriber. In event-based communication, especially in event-driven design pattern, the services that consumes the message, that is the consumer, does not need to know details of the message format. In event-driven pattern, the services just push the event to the topic, and then services then subscribe to the topic, will react to each event in the topic. Each event in the topic will be related to some business logic. So basically, in summary, in this particular type of communication, it is events which flow from producer to consumer. In the case of events, the message format doesn't matter, and hence the producer and consumer does not need to agree to the common contract of the messaging. That is the event-based communication. We will be covering this event-based communication in the event-driven design patterns when we are going to cover the design patterns used in the microservice, which is a very frequently asked interview questions. Now, how asynchronous communication and synchronous communication works? Which do you use in your project? What is the pros of using synchronous communication or asynchronous communication? And when to use which type of communication? We need all those to be covered in the next part. If you want me to cover more such, and you want me to cover the live examples of Kafka and GraphQL and gRPC, you have to let me know in the comment section. Thank you. Hi guys, welcome to Code Decode. Today we will continue with our microservice communication session.
Please like, share and subscribe to support us, and we are setting a like target of 500 likes.
We have already seen what are the ways to communicate with microservices. What is async communication? What if the message broker is down? What are types of async communication? That is point to point, that is ActiveMQ, RabbitMQ, and publish subscriber, that is the Kafka. What is event-based communication is also we have covered. Today we will see how asynchronous and synchronous communication works and what are the real-time examples of these both kind of communications. So this was our communication. This was a vaccination center. This was a slot availability microservice. User asks to vaccination center, can I book a slot? Vaccination center asks the slot availability for that particular vaccination center you are trying to book a slot for. If it is available, it books the slot and sends you an email or a text message on your phone that yes, your slot for a day or time, this to this is booked at this particular vaccination center. This was our flow when we started our microservice creation, right? So how does this internally works? So every application generates a message in the form of calls to APIs. The way the architect designs this communication affects the application's performance, resource consumption, and availability to execute the task. So whatever you decide, whether this should be a synchronous call or asynchronous call, what are these type of communications are going to makes a very big effect on your performance of your application. So when microservice communicates synchronously, it sits idle until it receives a call or response back. For example, a synchronous execution occurs during vaccination slot booking. A user decides to book a slot, generates a query to determine if slot is available to the slot microservice. It will wait until slot is booked in the vaccination center. So this should be a synchronous behavior because you should not have a mismatch between slot booking and slot availability. So when the user asks for the slot availability and slot registration, there should always be a synchronous call in the real time because you should not have a mismatch between slot booking request gone and slot response. So this is a very bad practice that you request that you should block a slot and you receive a message, okay, it is booked. But internally, when it tries to go asynchronously and see if there is no slot available, there is no way to get back to the user and say, oh no, the message that I have sent you previously was wrong. There is no slot available. So this cannot be at any cost be a asynchronous call. It should always be, okay, request went. It should check the database. If it is available, block the slot and send it back to the response as a user. And then after every process is done, you have your slot booked. You should always get a mail or a text message showcasing what is the place, where is the vaccination slot center booked for, what is the time, what is the date. Everything should be received in the text or the email format. So this is a real-time example of synchronous communication where asynchronous cannot work for you at any cost. Conversely, asynchronous communication allows code to continue to run even after it has generated a call or a response. So even after you have sent a response, after that also some processing is actually done. That is asynchronous communication. The asynchronous communication is particularly valuable for reporting and alerts. For example, sending an email or text message that your slot is booked to which particular vaccination center at what time, at what date. So here when your slot booking is done and a response is back, then again one call goes to the email service or the SMS service to send all the details of the book slot to the user. So the another user should not wait, or this user should not go ahead and wait for booking another slots or something. This text message or email service will be a very different service which can be called asynchronously. So you have the slot availability. This particular vaccination center service has all the details for the vaccination slot generated or registered. So it can internally go ahead and send a response that you will be shortly receiving the mail and the text message for the slot that you have booked. And simultaneously, in the asynchronous way, when user is doing something else, vaccination doing something else, slot availability doing something else, another service call is going to happen, which will call email service and text message service to send the notifications to the user later on. So this is a real-time example of asynchronous call where user or anybody should not wait for user to receive the mail. Mail will automatically be received with some mailing applications that you're using for the backend. User can start doing its own task. So that is asynchronous communication for you. That's the real-time application of asynchronous calls where that is reporting and alerts. Now you have seen the real-time example of both. You cannot use the asynchronous call while booking a slot. Because if you receive a message, yes, slot booked, and if there's no slot available, you will be in a trouble. So no asynchronous call in real time here. And the user should not wait to receive the email. The vaccination slot should be booked and user should do another task until then it should not be blocked. So this should never be a synchronous call. It should never wait for receiving a text message. It should continue doing other kind of stuff. So they have both potential pros and cons in the application. So it might be asked in an interview that you know when to use synchronous and when to use asynchronous call in real-time application. But what is the advantage of using synchronous? What is disadvantage of using the synchronous call? And the vice versa for the asynchronous ones. So you should know that. So the possible pros of using the synchronous call is it is very simple in design. You just have to create two microservices and interact them with the REST APIs and send response only and only when the response is received from the REST APIs. So this is very simple in design, and there is no complications in synchronous communication. But there is a very big performance impact because of synchronous communication, and that is that if there is a failure in any of the microservice, then your whole application will fail. So there's a chances of risk of spreading failures across these services. So if you have this microservice calling this microservice, when the response gets back, call the third microservice. If the first microservice is down, then even the third microservice call will not happen. And hence even the whole system can get down. So the chances of spreading the failures across multiple services is very high in synchronous communication. But there are many ways to mitigate this synchronous communication failures. You must always have the load balancing and service discoveries. So if one microservice is down, you should have multiple replication of slot microservice with like as in replication to slot availability 1, slot availability 2, all having the replicated code, but it is load balanced. So when multiple users hit to book a slot, it will be load balanced by a load balancer, and you have 3 instances of the slot availability microservice and it will hit, and to increase the user experience. But the disadvantage of asynchronous communication is, again, it is very complicated in architecture, and data consistency is a problem. Slot is booked, but internally your registration is cancelled. There was no availability. So there's a data consistency problem. But many advantages are available with synchronous communication. Very first thing is resilience and scalability. Even if your microservice second is down, even if this particular sort of availability is down, a message will be sent to the broker and it will go ahead and book a slot once the slot service is available. So there's a lot of resilience, but this doesn't work in our case. So what you can do here is you can put a message to the broker here that please send the email and a text message to the user that your vaccination center details are here. So you can put that message to the message broker, and even if your email service or text message service is down, once it gets up, it will pull the message from the broker and send the details to the user. And hence user is said, please wait, you will receive the mail after some time. So this is asynchronous communication. The advantages, resilience and scalability. It provides a better control over failures than synchronous setups. So even if the service is down, then also after sometime when it gets up, user will always get the notification. So there is better control over failures of over the synchronous setups. loosely coupled microservices. So here you have seen, if the slot availability is down, even vaccination center will not be able to respond back to user. The response is blocked. Even if the third microservice is to be called after the slot availability calls, that will also be disrupted, and hence this is very tightly coupled. Vaccination center has to be up, slot application service has to be up. If there's not up, the application is down. So this is very tight coupling. But in case of the asynchronous communication, even if the email microservice is down or the text SMS microservice is down, still your task will not be disrupted. Whenever it is up, it will send the notification to user, and hence it is loosely coupled. Now, a very important concept from interview perspective: when to use which type of communication. When do you use synchronous communication? When do we use asynchronous communication? When you are going to start a particular application designing as an architect. So when you start creating an application from scratch, you should always go with the synchronous communication. Why? Because in the pros, I have told you, synchronous communication is simplified. It is not complex. To understand multiple components in an application at the scratch is a very tough task. How they will communicate and how they will send message to each other is a complex procedure altogether. So introducing asynchronous communication will increase the complexity in the application, and hence you should always start with synchronous communication architecture to optimize the speed of evolution of the application. And once your application is stable, and when your microservice architecture starts to grow and becomes complex in functionalities, then you should switch to asynchronous communication. So how will you move from synchronous to asynchronous communication? Okay, we understand that when you start an application developing and designing, you should just go ahead and make all the communication synchronous, so that you will have less complexity in designing the communication between multiple microservices. But when you have your application stabilized and you have multiple microservice architecture stable, then you can go ahead and move all the services which can communicate asynchronously to move from synchronous to asynchronous communication ways. How will you do that? First of all, find all the possible communications within your microservices with each other and figure out if it is strictly needs to be synchronous. In our case, yes, vaccination center and slot availability registration has to be a synchronous call. It cannot work in a asynchronous way. Otherwise, user experience will be disrupted completely. So find out such kind of possibilities where you strictly needs to be synchronous. If it is really necessary, stick to the synchronous call. Else, like suppose here this message user does not have to wait for the emails and text message to continue booking another slot for the another user in the vaccination center, you can go ahead with the asynchronous call. So if response is really not necessary to proceed with other functionalities, then only go and convert that particular channel as asynchronous communication channel, like with ActiveMQs, RabbitMQs, and Kafkas. So in real time, you understand how to move from scratch to a well-stable application. From the scratch, go ahead, find all the components. So there's a 5 to 6 microservices. Go ahead, make all them synchronous. Once you are done with your designing purpose, there is no problem with the client. Go ahead and find out all these communication between multiple microservices, which does not strictly needs to be synchronous. If they are really needed, then only keep them synchronous. Otherwise, make all of them asynchronous, where the response is not necessary for the better user experience. Like example, logging, sending emails, sending text messages to the users, and many other such kind of things. So it doesn't need any user interference, and don't make users wait for long. Now, let's get to the conclusion for the synchronous asynchronous communication, because we have to quickly move towards the Kafka designing and architecture. So one of the traditional approach for communicating between microservices is to REST APIs. However, as the system evolves and the number of microservices grows, communication becomes complex and services start depending upon each other and become tightly coupled, which slows down the development teams and also makes the failures very common in such kind of tightly coupled applications. This model exhibits low latency. Okay, so you will get a very good user experience, but works if services are highly available. So you have to make sure all your microservices are all time available. To overcome this design disadvantage, new architecture aims to decouple the receivers from senders with asynchronous communication. Here we are going to use the Kafka-centric architecture. The low latency is preserved with additional advantage of message balancing amongst the consumers and the centralized management. To overcome the disadvantage of tight coupling, a loose coupling came into picture, and loose coupling is done through a message broker So one such very good example is Kafka-centric architecture. So when you are dealing with legacy platform, a recommended way to decouple a monolithic one, make it ready to move to a microservice implementation. You should always start with a synchronous, but as you grow with this architecture, go and implement asynchronous messaging to decouple the monolithic application with each other. So that was all about the conclusion part. We have many more things to cover, like difference between ActiveMQs, RabbitMQs. Then what is Kafka, pros and cons of Kafka, terminologies in Kafka, architecture in Kafka. And then we will go ahead and implement the Kafka in real time and see how this actually works when it comes to real time log aggregation with Kafka. If you want to know that, let me know in the comment section. I'll continue with this series ahead. Thank you.
Is Kafka and Zookeeper really that important? Many Fortune 500 companies use these open source products.
Hey guys, welcome to Code Decode. Today in this video, we will be covering the Saga design patterns for microservices Spring Boot interview questions. We will be covering what is Saga, why Saga, how Saga solves the problem, and what problem is actually solved by Saga. So let's get started. Please like, share, and subscribe to support us so that this video reaches to more of the people who are preparing for interviews. So first of all, why do we really need the Saga? We know that we as a developers, while developing some softwares, commonly face few problems. Now, few brilliant minds came to the rescue and created some really efficient, performance-wise great solutions to these common problems. And these solutions becomes the design pattern in our life. So microservices also have such design patterns. So whenever you are creating a microservice architecture, you are bound to face few issues as a developers. These few issues are those which are common to all of us. So few people came together and created few design patterns, which are the solutions, beautiful solutions to such problems of microservice architecture. So today we are going to cover the very first and very important problem, that is the distributed transactions. We will see the problem first. We will see what is Saga and what is Saga design pattern, and then we will see how the Saga design pattern provides a beautiful solution to such problems. This problem is actually getting started as soon as we move from monolithic application to microservice architecture. Today I'm going to take a very simple example of Swiggy and Zomato. Now whenever you log into the Swiggy or Zomato app, what you do? You choose your dishes, you add them to the cart, check out, make payments, get your order delivered to yourself at your doorstep, and once the delivery is successful, your order is marked as completed. Beautiful set of transactions, right? Now in monolithic application, it serves very good. Why? Because there is only one database, there are multiple tables like order table, payment table, delivery table, etc. Now everything happens in one single atomic transaction. Let me give you an example here. So in a monolithic architecture, what happens? You create your order, you make your payment, you get your order delivered at your doorstep, and then your order is marked as successful. So everything happens in a single transaction. Now if anything fails, the whole thing is reverted because it is atomic in nature, and the whole transaction is rolled back and your order is marked as cancelled if anything fails. Great, monolithic has no such issues because you can do it in a single same application. But when you move to microservice architecture, now you segregate the whole application into multiple different microservices, like order service to handle all your orders, payment service to handle and validate your payments, and delivery service to handle your deliveries at your doorsteps. But now the happy case goes like this. You have an order service, it accepts your order and it creates your order and updates your order table. As soon as it updates your order table, a next event is triggered which causes a payment screen on your app or your phone, and it asks you to make your payment. It validates the payment, and then a next transaction goes to the delivery service. When your payment is done, a delivery is scheduled, a delivery partner is assigned to you, and delivery is done at your doorstep. When delivery is done and the delivery partner makes it successful, your order is marked as successful or completed. This is the happy path flow in microservice architecture. Now, what happens if your delivery is failed or your delivery partner is not assigned to you? So, what is the worst case? When delivery is failed and no partner assigned to you, your payment was done, your money got deducted, and now you have no food. So, at this point of time, payment was done. This microservice has done its task. Everything is done. It has validated your payment. You have done your task beautifully. And now you are waiting for your food. But the Swiggy or Zomato does not have a delivery partner at 4 a.m. in the morning. what will happen? Your payment gone, your food is not there, worst customer service. What you will expect? You will expect that your payment should be reverted and your order should be marked as cancelled. For your payment to be reverted, you need a transaction rollback. But in microservice, this is a one whole standalone application. The application scopes and a transaction boundary starts here and ends here. So if your delivery is failed, only the transaction can roll back to this point, to the delivery point, and your delivery can be marked as failed. But your payment cannot be reversed because it was a part of different transaction boundary. It was a part of different application whole itself. So this is a problem. When your delivery is failed, a single local transaction rollback will not be able to revert your payment. So this was the problem. The transaction did get rolled back, but only the scope of transaction was in delivery service, microservice. The boundary for this transaction started and ended in the same application, that is delivery service. You cannot go back and ask your local transaction to make your changes to payment also. So now what about your local transaction to make your changes to payment also? So now what about your order and payment service? Neither your money is returned with the rollback nor your status is changed from waiting to failed or cancelled. Such a bad user experience, right? And this is not expected from a food delivery application. So this is a classic example where application has completely failed to manage the distributed transaction. What is a distributed transaction? A transaction that spans across the multiple microservices becomes a distributed transaction. This is a problem, and to handle such distributed transaction issues, Saga design pattern came into picture. Now let's see what is Saga, and then we will see what is Saga design pattern. So each of the local transaction which is responsible for making the changes in the same microservice becomes the local transaction becomes your Saga. So here we can see we have 4 Sagas. T1, T2, T3 and T4. These 4 transactions are responsible for their own specific transactions. For example, create an order and modify the orders table. This is Saga 1. Now open the payment page, make you do the payments, validate your payments that and update the payment tables. That is transaction 2, that is Saga 2. Deliver at your doorstep and update the delivery tables. Transaction 3, Saga 3. And after the order is delivered successfully, that's transaction 4, Saga 4. So that's the local sequence of sagas. Now, what each saga has a job to do. So each saga, you can see here, has 2 jobs. First, to modify your orders table, modify everything that is required in the order microservice, to create a new order, and then create an event in sequential order so that payment page can be opened. So 2 things. Do your local task, buy the local transaction, and trigger an event to the next microservice in sequence. Now, payment microservice saga is responsible for making the payment, validation of payments, and triggering an event for delivery if the transaction is successful. If the delivery is successful, then creating another event to mark the order as valid. So these are the 2 tasks of a saga, a single saga has to do. A single local saga has to update the current microservice and make required changes in the tables and in the data. Secondly, publish an event to trigger the next transaction for the next microservice in sequence. So this is Saga, a local transaction. Now, how Saga handles the failures of individual sagas. Now, how Saga design pattern handles this kind of issues. In this diagram, you can see there is no transaction handling, there is no transaction management for distributed transactions. So if delivery fails, there is no going back. Your delivery can be marked as failed, but your payment is not going to come back. Your order is not going to mark as failure. So this is not a proper transaction management for microservices. Here we have to implement a Saga design pattern. Now how your Saga changes this whole flow and makes it successful is here. You have an order service, you have the payment microservice, you have a delivery microservice. Now Saga 1 comes, it generates a create order event, modifies the order service with all the data and tables required, and hits the created order event. Now the second thing comes is the payment microservice is invoked with that event. Now the Saga 2 comes into picture, which is the local transaction for the payment microservice. Changes are done, payment is validated, and a new event is triggered for delivery microservice. With that trigger, another microservice local transaction Saga is invoked, delivery is done successfully, and when done, a transaction 4 with the event is triggered and order is marked as completed. But what this was a success flow, great, the same as we had there. But Saga invents a failure flow. Failure flow says you have to have a revert event also when the things fails. So whenever your delivery fails, not only the Saga responsible for delivery microservice rollbacks everything done in the delivery microservice but also raises an event called as delivery failed event. Now, this delivery failed event is responsible for triggering another event in the previous microservice in the backward direction, which is reverse payment event. Now, this reverse payment event is responsible for reverting the payment you have done so that your money that has got deducted gets added into your account. So, this is a revert event. Now, when this is done, the revert event is responsible for triggering the cancel order event, which is going to mark your order as cancelled so that you can go ahead with the next order. So this is the failure flow which is added by the Saga for you. So each and every event or Saga is also going to be associated with a revert event. If anything goes wrong, then the current Saga is going to call the revert Saga, and the revert Saga is responsible to call everything in line from where it came from the start. So till the start, everything is going to be reverted. So if you can see, this is not a rollback, this is a revert. You will never be able to do anything called as rollback with distributed transaction. The only thing you can do is to revert what changes and what harm or what damage you have done. So you have taken the payment, you were not able to give a delivery partner. That was the damage to the client. So a revert payment is to be initiated, and the revert payment will internally initiate the cancel order event. So this the same flow which goes here will go in the opposite direction here. That's the failure flow for you. So Saga design pattern provides the transaction management by using the sequence of local transaction called as sagas. Each and every microservice has its own database and is able to manage their own local transaction in an atomic way. We know that one single application is capable enough to manage the transactions with ACID properties. But the problem was the microservice architecture. A single transaction traversing multiple microservices is not handleable. For that, Saga came into picture. So Saga pattern groups these local transactions and sequentially invoke one by one. So this was T1, T2, T3 getting invoked one by one. Each local transaction updates the database and publishes an event to trigger the next local transaction. But one thing that is added by Saga here is the very important thing. If even one of these steps is failed, then Saga patterns triggers a rollback transaction. These are the set of compensating transactions that roll back the changes on the previous microservice. So these are the compensating transactions. These are, it seems to be a rollback, but it is not a rollback. It is a compensation. Since it is not able to assign your delivery partner, it is compensating with you with giving you back the money. At least that much of app should do for you. That is a compensating transaction that rollbacks the changes done by the previous microservice and restore the data consistency. So that since you didn't get your food, you didn't get your money deducted, you get it back in your bank account. So that's the compensating transactions in Saga. How to implement. So this seems so good, right? I mean, wow, you are complicated, right? So we have two ways to implement the Saga. We need a single point of interaction between all of these microservices. That is for sure. So there are two ways, that is choreographer and orchestration. Now choreographer Saga design pattern says that you can coordinate with a single message broker. So client will say, create an order. Message broker will create an event, create order event. So that Saga will make all the changes for the order service and then release an event known as make the payment now. Order is successfully created. Now message broker will send the event to payment service saying, please validate the payment. Once the payment is validated, the payment service sends a message or an event back to message broker saying, okay, the payment is successful. Please go ahead and deliver that food to the client. The message broker sends an event to delivery service. Please make a doorstep delivery to the customer. The delivery service makes the changes, delivers it to the users and sends an event, order delivered successfully. So this is the choreography design pattern where there is going to be a message broker, which is completely asynchronous communication. And this is how they are going to communicate with each other. So choreography is a way to coordinate local sagas where participants exchange events without a central point of control. Now everybody is going to interact each other with this message. They're going to take the message, send the message. Choreography, each microservice also runs its own local transaction and publishes the events to the message broker. That triggers the next local transaction, and that is how the next transaction is initiated, that is through the message broker. There are so much advantages of this. This is very simple workflow, right? You just need one extra RabbitMQ, ActiveMQ or Kafka here. That's it, nothing more. So only few participants and no coordination logic. There is no additional service or Java class or any kind of additional thing added for maintaining or implementation. Now also there is no single point of failure since the responsibilities is distributed across Saga participants. So these are the Saga participants. After creating the order, if order service fails, the payment will be done and delivery will be there. So there is no single point of failure. But when it comes to orchestration Saga patterns, there is a single point of failure that we will see soon. So, but there are some disadvantages to choreography design pattern also. First of all, workflow can become very confusing when adding new steps. That is, it becomes difficult to track which Saga is listening to which command. Now, payment service is listening to order service, delivery service is listening to payment service, but it becomes confusing as in more and more messages will be here. It becomes confusing on who is listening to what and what transaction is being performed by that particular application. There is no backtracking. There is no track of who is listening what if something goes wrong, who has written to which Saga. Backtracking is very difficult. So this was a problem with choreography design part. Now there is also a risk of cyclic dependency where order is sending a message to payment, but payment is also requiring some message from order service. So there is a cyclic dependency problem that can happen because they have to consume each other's command. Now one is waiting for second command, second is waiting for first command. This becomes a cycle and there can be a problem in choreography design part. And also integration testing becomes very difficult because all of these services are running the simulator transaction. So testing of this also becomes difficult because you don't know which service is going to listen to which message and how it is going to react. So integration testing also becomes very difficult here. So came the orchestration design pattern. The orchestration Saga design pattern is a way to coordinate the Saga again, but in a very controlled and centralized manner. And there is going to be an orchestrator, which is again going to be a Java component for us. This orchestrator is going to handle all kind of events going here and there. And it is going to be a single point of connection for each and everybody here. So orchestration is going to be a way to coordinate between Saga with a centralized control, which tells the Saga what local transaction to execute. Now, orchestrator handles all the transactions and tells the participant which operation to be performed on event. So what is the task of orchestrator? First of all, to execute a Saga. Second, to store the state of each task. If the task is successful, trigger another event to next microservice in line. But if it is failed, then you have to call the revert transaction. So that task is also done by orchestrator. So it not only commands which microservice has to work, but it also commands if in case any microservice fails to do the task, then it has the responsibility to revert it till the start. So this is the main person who is going to be a centralized person going to command everybody and also going to manage the state. If successful, go ahead with another local transaction. If failure, call the compensating transaction. So it handles failure recovery with the compensation transaction also. So this is a single point of centralized task. So you give a call from a client to orchestrator, it sends, go ahead make your local changes. If anything goes wrong, report me directly. When something goes wrong, a revert transaction is created or else the next local transaction is created. So every command is going from orchestrator to each and everybody and they are not going to just listen to anything. Orchestration is going to give the command. They are not going to listen to any message present in a message broker. Now, what are the advantages? It is very good for complex workflows with many participants or new participant added over the time. So this is going to reduce your confusion in which microservice is listening to which particular command and doing what particular transaction. They cannot just go ahead and listen to any message present in the message broker. They are going to get the command directly from the orchestrator. This is suitable when there is a control over every participant in the process and control over the flow of activities. So here even you can backtrack because everything is going to be logged up with orchestrator. Orchestrator is going to log everything. So if you go through the logs, you can see what transaction is done after what. It also doesn't include a cyclic dependency because orchestrator is unilaterally dependent on Saga participants. Anybody is not going to ask or command anything to orchestrator. Orchestrator is going to command everybody. So nobody can come back to orchestrator or do something. That's not going to happen. So there is no cyclic dependency. There is unilateral dependency from orchestrator to participants. That is a command dependency. That's it. None of the Saga needs to know about any of the commands for other participants. There's a clear segregation between the business logic. But there's still, it looks so good, but still there's a disadvantage. That is, you have to create your own orchestrator who is going to coordinate everything. So there's an additional design complexity in implementation of the coordination logic of orchestrator. You have to take an extra step, create your own orchestrator and manage everything at single point. Also, this is going to create a problem because that single point will become an additional point of failure. Now, if orchestration is down, everything is down. Even the order service is up, even though the payment service is up, even though your delivery service is up, if your orchestrator is down, everybody is a dumb listener. So this is where the single point of failure comes into picture because orchestrator is the one who commands and manages complete workflow. If it is down, that's it. Your Saga design pattern is down. So that was all about the Saga design pattern, guys. There is also many more design patterns like CQRS design pattern, event sourcing design patterns, many more Saga design pattern, guys. There is also everybody is a dumb listener. Single point of orchestrator. You have to create your own orchestrator who is going to coordinate everything. So there is an additional design complexity in implementation of the coordination logic of everything. So if you go through the logs, you can see what transaction is done after point will become a is down. That was CQRS design pattern, event sourcing design patterns, many more design patterns. If you want to know about that, just let me know in the comment section. I'll create more such videos for you. Thank you. Hey guys, welcome to Code Decode. In this video, we are going to cover some top microservices scenario-based interview questions for 5+ years experienced people. So let's get started. Also, if you want to implement an end-to-end project with microservices, Angular, and all these technologies like AWS, Sonar, Docker, Jenkins, Argo CD for deployment, CI/CD, RESTful web services for communication between microservices, and many more things for end-to-end project, you can have a complete implementation given at our Udemy course. Link will be given in the description bar below. Now let's get started and cover some scenario-based interview questions for 5+ years experienced people. How would you design and implement a microservice? So whenever a project is getting started, the first thing is the requirement gathering. Now you know that whenever we have a new project coming into our bucket, we might not have end-to-end every requirement in our plate given by our clients. In that scenario, how will you directly decide what should be the microservice bounded context? If you have an e-commerce website to be designed, how would you decide you should have payment microservice, order microservice, user microservice, and so on? There might be changing requirements now and then by the client, and your bounded context might change now and then. And hence your microservices context, their boundaries will also change. So whenever you are asked to implement a microservice architectured application, you should always start with monolithic one. So what we should do is to start with a monolithic application, put everything which is bare minimum requirement given by the client, create a minimum viable product, show it to the client. When you have the proper approval that yes, this is what the client needs, then only think about microservice architecture. So the first thing is always start with monolithic and create a minimum viable product. Second is now you should start planning how to implement a microservice. So now you should have your team organized in a perfect way. So you should have proper number of development team, DevOps team, testing team, and many such teams. Now once you have organized your teams in the perfect way, now you can split your monolithic one to the microservice architecture. So by till this point, you are actually planning everything and building the blocks for creating a proper microservice architecture with proper requirement in place, with proper team in place who are going to develop those microservices. So the third part is to split your monolith one now to the proper microservice architecture. So how will you do that? You will define proper bounded context. Like this is going to handle the orders for me. So that is order microservice. This microservice is going to handle all the product catalog for me. That is product microservice. So you have to divide each and every major requirements into bounded context so that you can share the data between them and handle the duplicate data efficiently. Now, when you have multiple microservices in place, the important part is how will you communicate between them. So while splitting only, you have to decide, you have to use synchronous communication between these microservices or asynchronous communication or the combination of both. So you can have RESTful communications with smart endpoints and dumb pipeline principle. That is, you should have the proper APIs and microservices in place to handle all the business logic and data transformations. And for the RESTful APIs, use the HTTP pipes who are not going to do any business logic, just going to transfer your request from client to server. So that's the way for communication synchronously. Or you can have asynchronous communication using queues like RabbitMQs, ActiveMQs, Kafkas, and many more such things. So now when you have done these things, you can have the service interactions with each other. You can have your data in place, like you have to decide you want to have one database per microservice or you have a common database for all the microservices, which is not a good idea though. If there is a need for that, you can go for that. So in the third step, here is the major task to be done. When you have to decide the bounded context, you have to decide the way how your microservices communicate. You have to decide how many database per microservice has to be decided. So this point is very important. Now, when you have every microservice in place, you have proper team working into these microservices, you have the communication properly done. Now the fourth step is you have to make sure that your microservice architecture do not fail.
If you want to become a pro Python developer without having any prior knowledge on the subject, then join our...
So whenever these microservices comes in production environment, most of the time, if one of the microservices fail, multiple microservices might get affected because of one of the microservice failure. So you have to focus on resilience, service responsiveness, recovery, and message handling. All of these can be done with multiple inbuilt integration tools like, for example, Haze, Streaks, and many more. So now when everything is done, you have to plan for your failure management so that you provide a proper responsive good performance application to the client and they do not get internal server error 500 exception and such exceptions when your microservice is down. Now when you know that your microservices will be available 24/7 without any failure, now you have to emphasize on your testing part, because now your testing will not be simple unit testing with JUnits and everything. Why? Because your logic is divided across multiple applications, multiple microservices. So how will you test the whole system end to end? How will you make sure that yes, when you place an order, a payment is done, but if your order is cancelled, a payment is reverted? How would you test this end to end flow with code written in different microservices? The way to do that is the system integration testing. So integration testing using BDDs are the ways to manage the testing between multiple systems. So testing becomes a very complex task when it comes to microservice architecture. Also, remember to use CI/CD for deployment process, because deployment for monolithic is very easy. You can deploy it one way. But when you have multiple microservices, deploying each and every application standalone by yourself is a very difficult task. By making it automated using CI/CD, it reduces the risk of release failures like prod failures, and you can actually focus on just development and running your application rather than remembering what wrong you have done while doing the manual production deployment. Also, continuous delivery makes sure that you have all the acceptance tests passing before the production is live. so that you actually passes all your unit test cases, all your BDDs, and everything is passing before you are on to the production. So these are the ways you always have to prefer while implementing a microservice architecture. Now, a next scenario based question is, you have microservice architecture, you have monolithic architecture. Explain the scenarios and situations where you will prefer microservice over monolithic architecture, or you will focus more in developing monolithic one rather than moving to microservice architecture. So which is better in which scenario and why? Now, first, when you have a monolithic architecture and you want to move to microservice architecture, the great example is e-commerce website. Now you have an e-commerce website with millions of users. Your application is built on the monolithic architecture. But when the business grew, more and more people and users comes in, it will provide you more flexibility for technology choices. Now, for example, your order that each team to complexity. If you have everything in one single architecture, if your payment service fails, but your other microservices like product catalog service, order service, everything is working fine, then the complete system doesn't go down. Only a sub part of that particular whole system goes down at a particular time, which gives a better user experience. In that case, also microservice architecture is preferred. Now, the scenarios where monolithic architecture is preferred over microservice architecture, which is very rare, because there are very few scenarios where monolithic is better than microservice architecture, because everybody needs modularity. But there are still some situations where modularity is not that much required. For example, in a bookstore. Now, what do you do at a bookstore? You just select a book, read it then and there, and put a review. The very minimal thing is what you are developing. So here you have very limited complexity. Basically, your online store is very much straightforward. You don't have multiple things as the requirement into that particular application. Now, breaking into multiple microservices will not produce rather advantages, but will actually add complexity to your simple requirement. So when you have very simple requirement, then do not go for microservice architecture because it will add complexity.
Want to build your own version of ChatGPT? Join us for this amazing opportunity where you can win over 8 lakh rupees in prizes. That's right, Langflow Hackathon, which is happening exclusively for India, where you are going to build AI applications, and we're going to provide step-by-step instructions on how to build your first AI application. You might be a beginner or you might be an expert. Everyone has a chance to win. The only thing you're going to need is a GitHub account. You're going to sign up with the link below and get started today.
Looking to take the next step in your career? Then you have to get this AWS course on Udemy. It gets you up to date on the latest tools and techniques so you can learn AWS fundamentals and pass your exam. Take this course at your own pace, on your commute, after work, so get this course now.
Also, sometimes the microservice architecture do reduce the speed also. That is when if you have multiple microservices, now if you want to change something which spans across multiple microservices, for example, there is some change which actually impacts my order service also, my product service also, my payment service also. Then first one team changes, then the second one, then the last dependent team changes. So first you have to plan the dependent changes, then you have to deploy the dependent changes in the particular order. So this actually reduces the speed when the change actually spreads across the whole microservices. In that case, monolithic is advantageous. Also, when you have a poor client, basically they do not have money to give you. So when you have the resource constraint, you do not have money, you cannot actually have proper resources for your development, deployment, and maintenance. Like they do not have money for your AWS. They cannot afford that. In that situation also, you have to go for monolithic one. When you have limited resources and you cannot invest in the architecture as it is not cost effective and feasible for you. Next, performance. Microservices for sure does introduce some performance overhead, and that is because inter-service communication. If you have everything in one particular application, you do not have to call another service, wait for its response and come back. So this actually adds some
latency and performance impact on your application. So when you don't want that, go for the monolithic one. Also, if you have a very small team or you have suppose a single developer, now if you divide it in multiple microservices, he'll be so confused like which code is written in which particular microservice. He will be end up working in multiple applications simultaneously, adding up so much overhead to that single developer. So when you have a constraint on the team size, you have a small team, and giving all these applications to one single developer is such a bad idea. So when you don't have the proper team size, you have less resources in terms of team also, then also don't go for microservice architecture. Also, transitioning to microservices actually have a learning curve. You have to understand how inter-service communication works, how pipelines will be working, how data consistency will be working. In all these situations, you have to have a learning curve. When you do not have that time for the learning curve for your team, do not go for microservice architecture. Stick to the monolithic one and give the things on time to the client before an escalation comes to your part. So the situations are very different for monolithic and microservice architecture. You might want to go for microservice architecture, but you do not have proper resources, you do not have proper team, you do not have proper learning curvature time. In all those scenarios, you actually should not go for microservice architecture. Stick to monolithic one, give minimum viable product that is required by the client, and complete your task then and there. Now the next question can be, how do you make sure a microservice based application can handle more users as it becomes more popular? Now, for example, you have created some application, you have made it live. Initially, with your client, you have very few users coming to your application since it's a very initial phase of your product. But as and when your product gets more and more popular, for sure, more and more users will be attracted to your application. In that case, for example, in normal days, the Flipkart, Amazon, these apps will have less users in a normal day. But when you have the great festival sale coming up, you will have more and more users attracted to Amazon and all. Then how will you handle n number of users simultaneously hitting your application and increasing the load on your instances? How will you handle that? So what you can do is you can load balance your application. So when you know that more people are coming to your application, you can load balance. You can have multiple instances of your services, and rather than overloading one single instance, you can rather implement a load balancer and evenly distribute all those users among multiple instances so that you have better user experience. They do not have to wait for your response from your server because you will have multiple servers responding to multiple users simultaneously. This prevents overloading of single server and ensures the better performance and better user experience to your users. Next is horizontal scaling. Now, what is horizontal scaling? That is adding more and more instances to your service. And without the horizontal scaling, you cannot do the load balancing. So obviously, horizontal scaling is required when the user load increases on your application.
Escape work chaos. Get flat 25% off on hotels with Clear Trips Big Travel Sale.
Then auto scaling. Nowadays, most of the cloud providers provides more and more auto scaling feature to you. That means they automatically add and remove instances in the real time to optimize your resource usage and costing. So what they do is when you have the sale going on, you have more users, they automatically add the more and more replicated instances to your application. And when the sale is done, they will remove those resources so that you are not charged for those resources which are empty and not serving any user, but still is there on your system. So that's auto scaling. Then caching, you can implement caching also on your services, which will help you access the data very quickly and you do not have to wait for the response from the server. You can have your own cache maintained and serve the static data to your users quickly. Next is database scaling. Now there can be a case that you will have database also to keep your data
for your application. If you have multiple instances but only one single database, then multiple users will have to wait to access that single database. Better if you have done the horizontal scaling, also focus on database scaling, because many a times we focus on making the instances scalable, we forgot to scale our database, and that is where the bottleneck comes. The bottleneck caused because of database will actually reduce your performance. So if you're focusing on instance scaling, also focus on database scaling. Also, you can do the asynchronous processing. Many a times when we start creating an application, we do the REST API implementation or the synchronous communication between services. But to increase the performance, to ensure the quick response, you do not have to always wait for the response from your service to give the response to the user. For example, when you have placed an order, you have to send an email. So rather than waiting for the proper email sending to the user and getting the response that the email has sent successfully, then telling the client that yes, your order is successfully placed, you place an order, you put it in an asynchronous queue, Kafka, RabbitMQ, ActiveMQ, any of the queue, and just send the response to the client that it is done. Because in the end, the email will for sure be sent if the service is up and running. In that case, you do not have to do the waiting for the email procedure. You would rather quickly send the response to the client, ensuring that you have better user performance by doing the asynchronous processing of emailing. Now, the next question will be, how do you handle data consistency in a microservice architecture? Now, let's first understand what the question the interviewer is trying to ask you. What is data consistency? I'll give you an example. You have an e-commerce website where you can place an order, get the payment from the client, and place an order successfully and send an email to the client that your order is successful. Now, the three microservices that you can barely see here is that you have an order service to take an order, you have an email service to send an email, and in between you have a payment service to get the payment. You can place an order from the order microservice, then you take the payment from the client, and when the payment is successful, you send an event that order is successfully placed and you send an email. Now, in this case, if the payment is not successful, if the balance is not sufficient in the card or something wrong happened with the payment, how do you make sure that data is consistent? That means if the user has placed an order and the payment is not successful, then you should roll back the order confirmation done in the order microservice. If the payment is failed, then order is also has to be cancelled. How do you make sure this data consistency? So you have multiple ways to handle data consistency in microservice architecture, but always there will be the balance between consistency and performance. If you make sure that your data is always consistent, then for sure the performance will be lagging. And if you want better performance at any cost, then for sure your consistency will be lost somewhere for some time. We have a way of synchronous communication. When you place an order, the order service will give a call to payment service that get a payment, and till then the user will be waiting that order is in process. That is synchronous communication. You will not get the immediate response if you have the synchronous communication through REST APIs or gRPC. But when the response comes that order is being placed successfully, that will be the case only when your payment is successful. That is synchronous communication. So here you can see that there is very strong data consistency. This will never be the case that you will get a message that order is placed successfully, but the payment is failing, because your order placed successfully message will come only when the payment is successful. So that's synchronous communication, and that is having a very high data consistency. But there is a problem. Your user will be waiting, having a message, order is in process, until the payment is not done.
मॉमी ग्रुप्स, पेरेंटिंग वीडियोस, अब किस को फॉलो करूं? सॉफ्टेस्ट डायपर के लिए बस अपनी बेबी को फॉलो करो, क्योंकि सिर्फ पैम्पर्स प्रीमियम केयर को मिलता है इनका अप्रूवल। इसका डबल लेयर सॉफ्ट बेल्ट और 360 डिग्री कॉटनी सॉफ्टनेस दे अल्टीमेट कंफर्ट। पैम्पर्स प्रीमियम केयर, इंडिया सॉफ्टेस्ट डायपर।
That is synchronous communication, which is very sensible also. You should not get order placed successfully until unless you have not the payment successful. Second is asynchronous communication. Now, if you have placed an order successfully, you have also made the payment successful. Now you have to send an email. So do you want to show your user that order is processing when you want to send an email but the payment is successful? No, you should not keep your user waiting for the email processing. What you can do is when the payment is successful, just send the response back to the client that your order is placed successfully. But do not wait for sending an email to the user also. What you can do is you can send an email through the asynchronous communication. So first you place an order through order microservice. You do the synchronous communication and wait for the payment. When payment is successful, do not wait for the user to have the email sent successfully. You can do it asynchronous communication with the email service and send the response to the user, your order is successful. Later on, put a message or email message to the queue like ActiveMQ, RabbitMQ or Kafka, and in the background send an email to the user. So this is how you do the asynchronous communication. But you can see that if you would have waited for the email procedure, then your user will be waiting for a long time, and that is bad performance. But in asynchronous communication, you send the message to the queue and send the response to the user for the quick response and order is successful. That's how you get the better performance, but you lag in the consistency. How the consistency is lacking? Because email is not yet sent. There might be a case that your microservice gets down, though even the order is successful, your email is not getting sent to the user. That is how your consistency is breaking. Your order is success, but your mail is not sent. But as soon as your microservice gets up and running, the email microservice gets up and running, eventually you will get the consistency. Eventually, after some time, the email will be sent to the user. So temporarily, there is some consistency lagging in the order successful screen and in the email notification. But later on, you will be getting there. The third is CQRS, that is command query responsibility segregation. Here what you do is you segregate your command or updation to the data and your query in two different databases and microservices. So what happens is whenever user come to query, one database and one microservice will always respond to it. But whenever a request comes to update the data, delete the data, add the data, that is a command for the data, then a segregated microservice and database will be responsible for it. And later on, whenever the user comes to query something, a query database will be responsible to respond, and whenever a command comes, a command service will be responsible for response to the user. But how the consistency is maintained? There is always a communication between the command microservice or a query microservice. They interact with each other with a synchronous or asynchronous communication. Usually it's asynchronous communication done through the queues. There might be a case that when a query comes from the user, it might get some stale data when you are doing the asynchronous communication between query microservice and command microservice. That's the way to handle the consistency, maintaining a proper, better response to the user. Also, you can have the event sourcing, means that whenever a data change comes, it is captured as a sequence of event. That is event sourcing. That means whenever first an order comes, then a request for the payment comes, then the request to the email sending comes. All these three comes as an event, three different events. And whenever your payment fails, then you roll back to the previous event also. That means when you create an event, that place an order. Then you create an event, ask for the payment. If the payment fails, then you roll back to the previous event and says that also cancel the order because the payment has failed. That's the series of event you can manage for the data consistency. Then you can have the distributed transactions also to maintain some data consistency in the microservice architecture. But remember, whenever you do the distributed transaction, what you always do is synchronous communication. For example, in the 2PC, you always do the synchronous communication. In that case, you always have less performance, but a best data consistency because it is synchronous. But when it comes to Saga design pattern, you try to implement it using asynchronous communication using Kafka, ActiveMQs, RabbitMQs, and queues. So you have sequence of local transactions in the Saga design pattern, where each of the data maintains its own data consistency. But if anything fails, you roll back the local transactions. That is the Saga design pattern using the asynchronous communication. we have created a complete separate video on Saga design patterns and CQRS. You can get the link in the description bar below for better understanding of how local transactions and how rollback happens in the Saga design pattern. But this always uses asynchronous communication, so you have better performance but less and temporary data consistency. How? Because initially you have one transaction done saying the order placed successfully, but when payment is failing, then you have to roll back and say, sorry, your order is cancelled because your payment has failed. That is Saga design pattern with the local transactions and rollbacks. Also, these were the ways to maintain the data consistency.
खुद का किराया ऑफर करो या ड्राइवर का वो ऑफर चुनो जो आपको पसंद आए। अब ऐप की नहीं, आपकी चलेगी।
But there must be a way to make sure that your data is actually consistent across microservice. That can be done using monitoring and logging. So you have to monitor and properly log and detect and diagnose your data consistency issues early. You have multiple distributed tracing tools, centralized logging tools to handle and find out anomalies in the data across multiple microservices. So when you have proper monitoring and logging, it makes sure that yes, your data is consistent across microservice. But what happens if the monitoring and logging says your data is inconsistent? Then you need conflict resolution. So there are multiple strategies to handle the conflict if they arises in the data in different microservices. They may involve time-based conflict resolution, or even in some cases you have to intervene with a proper human intervention. Say suppose if you have a production having the conflicts, then you need a human intervention to resolve that conflict in the data so that the users are not impacted. So these are the ways to handle the data consistency. This is the way to monitor and log whether data is actually consistent. But if the logging says data is inconsistent, then you should have a proper conflict resolution to make sure user is not affected. So that's the way to manage the data consistency. Now, since you have used a 2PC, you have used a Saga design pattern, the next question may come to you is, what is the difference between Saga and two-phase commit? And which will you prefer in which situation? So the main difference between two-phase commit and Saga pattern lies in the way these actually work. The 2PC works with the synchronous communication, while Saga works with the asynchronous communication. Now, for that, first you need to understand Saga and 2PC. 2PC works with the synchronous communication where there is one coordinator. Say order service is the coordinator. The payment service and the email service becomes the participants. Order microservice sends a prepare request to payment service. When the payment service says yes, payment is successful, you will have a vote to commit or vote to abort based on the payment is successful or payment is unsuccessful. In both the cases, the order microservice will be as a coordinator will be waiting for the response from the payment microservice. So this is a blocking scenario. That is a synchronous scenario. So the way how the two-phase commit in Saga works is different. Saga has local transactions, while the two-phase commit has the messages going here and there as a prepare and the vote to commit or vote to abort. For if you want me to cover the two-phase commit in detail, just let me know in the comment section. I'll create a very separate video for this. And for the Saga design pattern, a complete separate video is already present on the channel playlist. The link will be given in the description below. Now, to understand what is the difference between two, you should understand that two-phase commit works with a synchronous communication, where until the payment is not done, the order service will be waiting. But if you would have used Saga design pattern in the e-commerce website, then you will see the asynchronous communication where the user will see the order is placed successfully and later on the payment is processed, which is not a good case. But if you have used Saga design pattern, this is how it will be working. And if the payment later on gets failed, then you will get a notification that since your payment was failed, your order is now cancelled. So even though you have get the order confirmation, later on you will get the notification for order cancellation also. That is the rollback of the local transaction. That's asynchronous communication. Two-phase commit, because it is synchronous, it is blocking. Blocking means if in any case your payment service is down, then your order service will not get the response for your prepare message. You will not get vote to commit or vote to abort. In that scenario, you will have a blocking situation. But when it comes to Saga design pattern, it's a non-blocking situation. When it comes to consistency, two-phase commit, because it is synchronous, it is very consistent. You will get the order confirmation only and only when the payment is successful. But in the Saga design pattern, if you will get the order confirmation as soon as you place an order, but your payment is successful or not depends upon the payment microservice. If it is successful, your order confirmation message remains as it is. But if it is unsuccessful, you will then have a rollback. That means you will have the notification your order was cancelled because you didn't do the payment. That is, eventually your system will be consistent, but at that point of time you will have a data inconsistency because you get a message of order confirmation but your payment is yet to be done. If the payment is successful, your system is consistent, but it is unsuccessful, you become in an inconsistent state of having the message of order placed successfully but the payment is unsuccessful. Eventually you will get the consistency. That's Saga design pattern. The two-phase commit adds complexity because you need one transaction coordinator. You will have one message traveling of synchronous communication that prepare. You will have messages like vote to commit or vote to abort. So lots of complexity is added by two-phase commit, while that is not the case when it comes to Saga design pattern. It is usually less complex than 2PC. The two-phase commit also adds performance overhead because the synchronous communication is needed and additional communication and coordinator is required, which is not in the case of Saga, and hence it's better in the performance because it is much more simpler. But the best part of two-phase commit is it is a very strong data consistency, but it comes with the cost of performance overhead. When it comes to Saga design pattern, you have a temporary inconsistency that I have told you already. When you have the order placed successful message, but a payment is unsuccessful, then you have a temporary inconsistency, but because of this you have a better performance. So it completely depends upon you which to use when. Whenever it comes to e-commerce, I'll always prefer two-phase commit or distributed communication, but when it comes to emailing system, then Saga pattern is also good. It depends upon your requirement. You want to use two-phase commit with synchronous communication or asynchronous commission is Saga design pattern. So that was all about interview questions for 5 years experience in microservices. If you want more such questions for 7+, 9+, or the architectural level questions, just let us know in the comment section. We'll create more such interview questions for you. Thank you.
ये सैंडविच कितना बढ़िया है।
इसमें ना ऐसी वाली चीज है।
Hi guys, welcome to Code Decode. Today in this video, we are going to start with the Kafka introduction. So let's get started. Please like, share and subscribe to support us. And we are setting a like target of 500 likes. What is Kafka? Apache Kafka is a publish, subscribe, fault tolerant messaging system. It is fast and scalable and distributed by design. In the previous slides, we have seen what is point-to-point and what is publish-subscribe models in messaging systems. So Kafka is a publish-subscribe model, while ActiveMQs and RabbitMQs were point-to-point messaging systems. It was initially thought of as a message queue. It was initially created by LinkedIn in 2011 as an open-sourced messaging communication system with multiple publishers, multiple subscribers. But later on, it was found that Kafka is much more to just a messaging system. So in the later years, Apache took over it from the LinkedIn, and the community evolved Kafka to provide multiple capabilities. The very first capability remains the same, that it is publish-subscribe model, just like a messaging queue in a messaging system. So it is by default there created by LinkedIn. Later on, it was modified to have the storage systems also, so that messages can be consumed asynchronously. Kafka is going to write a data to a disk structure. So there is some storage system available where the data is going to be written and is going to be replicated in multiple brokers and multiple disk areas to be fault tolerant. The third important thing is that a very important modification done to the capability of Kafka is that it was enabled for stream processing with Kafka Stream APIs. So multiple APIs were introduced later on in Kafka to be able to do stream processing, which enables complex aggregation and joins of input streams into a particular output stream of processed data. Too much of theory, we will see how Kafka is capable enough to do all those things when we are going to see the architecture of Kafka. Just by going and implementing a project with Kafka is not enough. Though it seems very easy to just go and implement Kafka and say, okay, I know everything. But when you go to an interview, they'll ask you multiple things. Why it is fault tolerant? Why did you go to Kafka? Why not ActiveMQs, RabbitMQs? How Kafka is different from ActiveMQs, RabbitMQs? And what are the pros and cons you have found while implementing Kafka and moving from Apache MQ and RabbitMQ to Kafka? What good and what bad have you seen in your journey? So to implement and answer all those questions in an interview, you should know the basics of Kafka first. The traditional messaging models are queues and publish subscribe models. So in queue like ActiveMQ and RabbitMQ, each record goes to only one and only one consumer. So this was producer and this was a consumer. Whatever the producer produces is going to be consumed by exactly one consumer. And as soon as consumer consumes it, the message is deleted from the broker. While in the case of publish subscriber, all the data is written to some disk storage, basically a storage area. And subscribers or the consumers pulls that data from that particular hard disk, but does not remove it. Why? Because that particular message is not just meant for consumer one, but it is meant for multiple consumers or subscribers who are subscribed to that topic. So the subscriber does not delete that data while reading it, while the consumer deletes the data as soon as it reads it. So that's the very big difference between ActiveMQs and Kafkas. What is the advantage you found while you have moved to Kafka? A very first advantage we have seen while moving from REST API to Kafka is the loose coupling. That means neither services know about each other regarding the data update matter. So basically, your producer does not want to know whether the consumer is up and running and how many consumers are there. Producer will just push the data on the topic and will forget about it. While it's the task of multiple consumers to consume from the particular topic. Durability guarantees that the message will be delivered even if consumer service is down. So even if your consumer service is down, your data will be stored at that particular disk space from where whenever the consumer gets up and alive, it will fetch or pull the data from there. All the messages will be present in that disk. It will not be deleted. Third, scalability. With Kafka, you have immense scalability and fault tolerance. The messages get stored in a bucket called topic, and there is no need to wait for the response to the producer. What it does is it just pushes the data to that particular topic or the disk memory area and forgets about it. It's the task of multiple consumers to consume that from that particular disk space. So this is how you do asynchronous communication. Fourth is flexibility. The sender of the message has no idea who is going to consume it. So your producer does not know how many consumers you have. Meaning you can add any number of consumers without doing anything else. So you can add subscriber 4, 5, 6. Publisher won't even know about how many subscribers you have. It will just publish the data. And these multiple subscribers will pull the data from that particular storage area in the memory. While in the producer consumer, they are very tightly coupled. Each consumer will consume the data from the topic and deletes it from there. Now, with great advantages comes great disadvantages also many a times. So, whenever you move to Kafka, you have to make sure that your application really needs Kafka. Now, Kafka seems so easy, right? There is one publisher, multiple subscribers, so easy. But when you go to the architecture, it is this complex. There is a cluster, there are multiple brokers as a topic has multiple partitions. These are multiple consumers, there are multiple producers going to produce at particular topic in which particular partition it has to decide who is going to handle all these clusters as a zookeeper. So it doesn't seem easy, does it? No, it doesn't. So with this particular high level of advantages with Kafka comes a great responsibility, the responsibility of developers to understand how these messages actually flow, so that if something falls back, you should have a proper approach to handle the failures. Because it is so complex, you should have a particular architectural knowledge before using Kafka. You cannot just go and implement just like you can do an ActiveMQ. Create a producer, create a consumer, great, your life is so easy. No, it's not that easy when it comes to Kafka. If something breaks, you have to understand where the particular message is, why is it breaking, which particular consumer is not able to get the data, where the message is lost, because the chances of you losing the message here in Kafka is really high. So there's a less message visibility. When you comes to consumers, there are multiple consumers. So how will you track all those messages? Where are they going? With the multiple subscribers, you can't have the clear visibility on which particular consumer is facing issue in consuming, or which particular producer has produced it but not available to consumers. How will you do that? How will you manage all your messages? How will you track your messages, or how will you log your messages? So there is something called as correlation IDs, which Kafka has given to us to handle such kinds of message visibility problems. It seems difficult, but as soon as you go ahead, understand the technologies, understand the architecture, it will be easy to answer such questions in an interview. If you have implemented Kafka in your project, you should have a very strong base to answer why. Why not ActiveMQs, RabbitMQs? Because for a very small project, ActiveMQs and RabbitMQs are good enough. Why did you took a step ahead and move to Kafka? So there are multiple reasons. We'll see the comparison and then you will be able to understand for your project which is better, ActiveMQs, RabbitMQs, or the Kafkas. So firstly, who created ActiveMQs? ActiveMQ was created by Logicbase and open source message brokers. Later it was donated to Apache Kafka, who continue to develop the code base for ActiveMQs. So now ActiveMQs are with Apache. Now RabbitMQ is owned by Pivotal Software Inc. and currently also it's still with them. While in case of Kafka, it was initially designed by and created by LinkedIn. Later in 2011, Kafka was open sourced and the further development was done by Apache to increase the capabilities of Kafka from not able to now. Point-to-point messaging system, we have covered that in the previous slide. Just to get an overview of ActiveMQs and RabbitMQs in Kafkas, ActiveMQ and RabbitMQ is a traditional messaging system that deals with very small amount of data. So if you have a producer which produces the data in a very small amount, go for ActiveMQs and RabbitMQs. They are point-to-point messaging. One or more consumers are connected to the queue, while the broker uses round robin to direct message to a specific consumer. So make sure only one consumer is going to consume the data from the queue, not the multiple consumers. There might be a chance that you have multiple consumers, but there will be an if-else condition, whether if the producer has some condition in the message, then consumer 1 is going to get the data, or other way around, consumer 2 is going to get the data. But only one consumer will get the data from the queue. While Kafka is a distributed publish-subscribe message delivery and logging system. Remember, it was publish-subscribe message delivery till it was with LinkedIn. Later on, its functionality is improvised by Apache softwares, and it has turned into not just a publish-subscribe model, but also to a logging system which supports streaming of multiple logs in the exact order in which it has produced by a producer, and you can log all of them of your logging systems. So that follows publish-subscribe model with message persistence capability. So here, as soon as your consumer consumes the data, your data is removed from the queue. So there is no persistence here. But it has to persist data in Kafka because multiple consumers are going to consume it. If first consumer itself deleted the message from the topic, others will not be able to read it. So there is a message persistence capability and hence storage is available there. Producer pushes the event stream to broker. So producer produces the data to the broker or the topic, and consumer pulls the data from the topic. So in subscription-based messaging, brokers broadcast message to all consumers who have subscribed to the topic. Now, a very important thing, when to use ActiveMQ, RabbitMQ, and when to go for Kafka architectural wise. So whenever you have exactly one message delivery and you have a very valuable message to be delivered to that particular client, go for ActiveMQ, RabbitMQ. Secondly, you have very small amount of data to deal with, not thousands of logs that you have to stream around in a particular logging system. Then go for ActiveMQs, RabbitMQs. But when you have a very high performance monitoring system, like you have to monitor what logs are there in your system, how your system is performing. Is there any kind of log.error that is being printed on your system? Then you use Kafka, and here losing a message is not that important. Once in a while, 1,001 message can be lost, then you can go for Kafka. But when you have a very valuable message, you cannot lose even single message, go for ActiveMQs, RabbitMQs. Throughput, it is a very lower throughput because each delivery message state is maintained. ActiveMQs, RabbitMQs make sure even single message is not lost and the message state is maintained. That is why ActiveMQ, RabbitMQ is preferred when your message is very valuable. While with a very high throughput with Kafka, because producers don't wait for acknowledgement from brokers at all. Leave the consumer. It doesn't even wait whether broker has consumed it or not, whether broker has saved it in the memory or not. It will just go ahead and do its task. In this particular case, the message might be lost because producer doesn't wait for broker to save that particular message in memory. It just leaves the message and go ahead with the another task. And hence, it is very high throughput. It is very fast, but your message might be lost. So broker can write message at a very high rate because it just bombards the broker with multiple messages and forgets about whether the broker is able to do its task or not. So if your broker fails, your message will be lost. And hence Kafka gives you a multiple redundancy option. And that is why here in this particular cluster, you can see multiple brokers. These are nothing but the redundant brokers. So your data is redundant and hence it is fault tolerant. So if your broker dies, your second broker is ready to get the data from bombarded from these particular producers. Order of message. ActiveMQ, RabbitMQ cannot assure any order of message to remain same. While in Kafka, it can assure the message retains the order in which they are sent. When you run a particular Spring Boot application, you see a console, right? So whenever you put logs, we just go ahead and say log.info, log.info, log.info. You don't think that you are bombarding the server with multiple logs. But it's task of Kafka to make sure that all the logs are maintained in the exact order in which that has happened. If it doesn't happen, then you will be in a problem. So there can be a case that I have an e-commerce website. So you have placed an order, the order is received, then order is checked in an inventory, whether inventory is present or not. If it is not there, send an error. Sorry, no inventory present. Now, if you do not retain the order, you can see the logs as, okay, order received, inventory sent, that there is no inventory present, and then you go and check the inventory. It will confuse you. You will not be able to debug the real issue. So that is why order of message is very important in Kafka because it is used in logging purpose also. In monitoring systems, it is used. So Kafka maintains the surety of order in which they are sent, while in ActiveMQ, RabbitMQ, you can get the message anytime, anywhere. So this is the disadvantage of RabbitMQ, ActiveMQ. Messaging type. Oh, this is very important part. ActiveMQs and RabbitMQs are push type. That means the publishers or the producers push the message to the consumer, while the Kafka is a pull type. That means multiple subscribers pull messages from the brokers. And that is why who has the responsibility to ensure the message delivery? Here the producer or the broker has the responsibility to make sure that messages are delivered. And hence it is a smart broker which makes sure your data is received to the consumer and consumer is dumb. While in case of Kafka, it's a task of consumer to consume the message from the topic or the disk area, and hence these are smart consumers who are capable to pull the data, and these are dumb brokers who just keep the data with themselves and will answer whenever you ask them for the particular message. So these are the dumb brokers, smart consumers. These are the dumb consumers, smart queues. Now scalability, you don't see any scalability in ActiveMQ, RabbitMQ. There are no horizontal scaling. There are no multiple queues to provide you with the replication data. But here scalability is available because both the replication of brokers and the replication due to partitions. So here you can see the replication of your data. So even if your one broker is down, another broker will be up. Minimum 3 redundant brokers are available in your cluster. As known, the throughput is very high for Kafka and hence performance will be high for Kafka only. So performance is very good and effective even if the new consumers are there, because producers don't have to think how many new consumers are there. They are completely loosely coupled. So the throughput for and performance is 1 million messages can be handled by a Kafka topic, while in case of ActiveMQs, performance is very slow. They can handle only 4K to 10K messages per second. ActiveMQ supports both asynchronous and synchronous communication, while Kafka for sure has to be asynchronous, because producers not even wait for brokers to save the data. How will it wait for your consumers to consume the data? It will not. The message retention part. I have already told you, as soon as your data is consumed by a consumer in queue, it will be deleted. So these messages are removed from the queue once they are processed and acknowledged by the consumer. But in the Kafka, it is not the case. Message is retained and will remain forever until there is a time to live. That is, there is a retention policy. So retention policy is 30 days. So Kafka messages are going to stay in your topic or in your storage area for 30 days. Until then, your consumers, when wake up any day, day 1, day 10, day 15, doesn't matter, it will get the data in the topic saved. So until your retention time doesn't expire, the data will be there. Developers have no other option. Kafka is not giving you any option to delete it. You have only one option to handle the time to live. That is the retention policy. If you have given the retention policy is 30 days, you cannot do anything to remove that data. Push mechanism is used by ActiveMQ, RabbitMQ. That means they are smart brokers. They are constantly trying to deliver the message to consumer and keep the track of their status, while they are dumb consumers. They just sit idle and wait for brokers to give them or bombard them with the data. So this is push from queue to consumer. Consumer sits idle, queues push the data to consumers in this direction. While this is a pull, subscriber pulls the data, and hence subscribers or consumers are smart while brokers are dumb. So dumb brokers and smart consumers, Kafka doesn't monitor the message for each subscriber whether they have read or not. Rather, it retains unread messages only, preserving all the messages for the set of time it is there. Payload size, there is no constraint for the payload in ActiveMQ. How much big data you will send, it will be able to capture and cater that. While the default is 1 MB limit for Kafka. This is a simple use case where you can use it, but when your architecture grows complex and you have very high throughput and massive data you have, then you go for Kafka. So that was a very high level difference between them. Now we have very important terminologies to be covered in Kafka. What is topic, what is cluster, what is producer, what is zookeeper, and even the architecture of Kafka is very important. So in the next video, we will cover all these high level terminologies and the architecture of Kafka in the next video. Just let me know in the comment section, else I'll skip all these terminologies and I'll directly go to the implementation if you want that. So you have to let me know in the comment section. I have the code ready with me. I have these terminologies ready with me. If you want to know about these terminologies, let me know in the comment section. Else I'll skip this and I'll directly go to the code base. Thank you.
Get 10% extra savings on flights and hotels with Supercoins during Cleartrip's Big Travel Sale.
টাটা প্লেট যে ডিলার আছে না, ওনার মেয়ে টিউশন টিচার তো তুমি খুঁজে দিয়েছিলে না? তোমার কানেকশন ইউজ করো না প্লিজ। দেখো না 1299 সেট টপ বক্সে আরো বেটার কিছু পাওয়া যায় কিনা।
এই বলু একটু সরুন না, নো নিড ফর এনি কানেকশন।
আরে টাটা প্লে নিজেই দিচ্ছে ধামাকা অফার, 3000 দাও আর
এইচডি সেট টপ বক্স, ডিশ, রিমোট সব ফ্রি।
ঠিকই শুনেছেন আপনি।
Hi guys, welcome to Code Decode. Today in this video, we will see how to implement Kafka in real time with a live demo. And then understanding this kind of architecture for Kafka will be much more easier after we know how this actually is internally working. So let's go and create a live demo first of how we can create producers, how we can create consumers, how to create end-to-end configuration for Kafka, and then let's understand how this actually works internally. So let's get started.
Please like, share and subscribe to support us, and we are setting a like target of 500 likes.
For implementation of Kafka, the very first thing we need is Zookeeper and Kafka installed for us. Now, since we are running all this in local and we are not using Docker at all, we will be installing all of these things in the local first. And then later on, when we are good with the basic demo for the Kafka, the producers and consumers, we will move to Docker later on, after this much is clear to us. So for installing the Kafka and Zookeeper, the link is here, and this will also be given in the description below. Just go ahead and install Kafka from this particular link, Scala 2.12, and you will have an inbuilt Zookeeper already installed with the Kafka. Now I have this already installed, so I've installed it in the software package. If you can see in the bin, you can see with Kafka you have Zookeeper already installed. So once you have done this particular step of installing the Zookeeper and Kafka, just by downloading it from here and extracting it at some folder location, you are good to go with the start of the Spring Boot project creation for Kafka. So the project setup for Kafka is, we need a Spring Boot project, then we need a Kafka dependency with a web dependency, then we need a controller to fetch the message from a client. So we are going to create an architecture where there will be a producer, where there will be a consumer, and in between will be a Kafka topic. Topics are also called as brokers, and brokers have internal partitions. So we need to produce something, and that producing message I'll be taking from the REST API from the client. So there will be a third-party client who wants to send some data to the consumer. So he'll hit the REST API. The REST API will contact producer and give that message to the producer. Producer will produce that message in the topic or the broker. and that will be subscribed by the consumer and consumer will pick it. So what we need is as a wholesome, then we need a Spring Boot project to have the producer, consumer and Kafka into it. Secondly, in the Spring Boot project, we need a REST controller, which will act as an interface between the client and the producer. So the task of that REST API will be to take the message from the client and send it to producer. Producer will send that message to the broker, and then we need a consumer who will subscribe to that broker. So first thing, REST API. Second, we need a producer. Third, we need a consumer. And fourth, we need the configuration settings for the Kafka implementation. So you need a controller, REST API. You need a producer who push the message to the topic. You need a consumer to listen and subscribe to it. Next, you need the properties file to have the configuration for the Kafka. At last, when everything is done, you need to run first the Zookeeper, then you need to run the Kafka server. And then if you try to hit something, you will be able to send that message from producer to consumer. So let's get started with a quick demo. Let's quickly create a new Spring Starter project. I can name it as Kafka demo. So this is a demo project for Kafka implementation. Let's go to next, and let's have the Spring Web as the dependency and Kafka as a dependency. We are not using streams. After a few videos, when we are good with the streams, we'll also create a video on streams and how to create streams and what all API they have added for the streams. So currently we have Kafka and Web, and let's finish it. So we have Kafka demo project almost ready with this. This is the main class which will run. Now what we need is a controller. So we'll create a package for controller and a class REST endpoint for Kafka message. Here this is a REST controller, so we will be annotating it with REST controller. Here we need a get mapping, get message from client. It will have a request parameter. I'll say it as message, and it will be of type string. We'll have a request mapping here, which will identify this controller uniquely. So it's an API for REST. So this is basically a REST API. In the get mapping, we'll have, say, a unique name as producer message. So this message is going to be a message for producer. So whatever you give as a request parameter here will be a message for the producer to send to the topic. Now our controller is ready, but we need a producer to produce the message to the topic. This is a task with some kind of business logic into it, right? So we need a service package. That service package will have two services, a producer service and consumer service. And similarly, we will have a consumer service. Now, producer service will be annotated with @ service because bean should be created for this. And similarly, consumer should also be a service. With this in place, we need to send something to Kafka, right? So we need a Kafka template. And it's going to have two parameters. First parameter will be the name of the topic and second will be the message. So the name of the topic will be for sure will be a type string. And similarly, the value will be also the string. And I'll name it as Kafka template. And I'm going to auto-wire it. With this, we have a simple method name as public void send message to topic, and it will have string message as a parameter. And simple, the Kafka template will be used to send the message to the topic. So it will have two parameters, the name of the topic. So you have to first decide the name of the topic. So let's make the name of the topic as code decode underscore topic. Fine. And let's send the message to the topic. So I can say my producer is ready. My producer is also Bean. It has auto-wired as Kafka template, and Kafka template is capable enough to send my message to the newly created topic. Great. Now the producer is ready. So in the controller, what we can do is we can auto-wire this producer, and you can use this producer to send message to the topic with the message that you will receive from the client. So this REST API is going to be hit by the client. It will give you a message in the request parameter itself as a get request. You are going to get that message and send it to the topic to the producer, which we have recently created. So this producer is going to call the Kafka template send method, which will internally send this message that you are sending as a parameter to the topic created as with this name. Now this is all good. We have the producer ready. We have our controller ready, but we need a consumer also, right? So consumer will be something who will listen to your Kafka topic. So there will be a method public void listen to topic, and it will have string message which it will read or consume from the topic. So this will be a received message, and I'm just simply going to print it. Great. But this method has to be annotated with something which will make it capable enough to read or listen to the messages from a topic, or which will make this class capable enough to be a subscriber to a topic. So we will have an annotation called as Kafka listener. This Kafka listener is going to make this class or this method capable enough to be a Kafka listener or a consumer to the Kafka topic. But it needs two things. That is topic. So basically you can have multiple topics to be listened to. So this is basically an array of topics you can listen to. I have one single topic here. What topic we have? This is code decode topic which we have created. So single topic is going to be listened and subscribed to, and a group ID. This is very important because this Kafka is made to be fault tolerant and scalable. Now, if you have hundreds of consumers listening to a single topic, it is for scalability internally divided into multiple partitions. Now, each partition is nothing but a replica of some data. To reduce the load from one single partition, the task of this group ID is to group these consumers into groups so that the load can be balanced in these broker, and not C1, C2 and C3 should not go and read from just first partition and bombard this first partition with multiple requests to read. Rather, C1 should read from first partition, C2 should read from second, C3 from the third, and so on. To make it load balanced, the consumers are grouped with the group ID. So if you have C1, C2 and C3 in the same group, say code decode group, then the data will be load balanced between C1 and C2 so that you do not bombard with the pull request for the data on this topic. Each consumer will read from a separate partition, and this particular partitions are equally balanced between all the consumers in a particular group. So this is why this group ID is very important. The group ID here is going to be, say suppose code decode group. Now our Kafka listener is ready. Our Kafka producer is ready. Our REST endpoint is ready. When all these things are ready, we need configuration for Kafka implementation, right? So in the main resources, we will be creating a new file named as application.yaml. You can also do that in properties file, but for the simplicity, I use this YAML file. 9092, this is for the Kafka default server port. Now, whenever we send a message from a producer through a template to a topic, it has to be serialized. That is, the string has to convert it into the type of bytes. Now, how to serialize the message and the value, the keys and the values to send it to the particular topic is through serialization and deserialization. So I'm denoting that both the type of key and value serialization should be a string serialization, because I want to convert a string to type of byte so that it can be sent to the topic to the consumer at the end. These are nothing but the type of serializations we are using for conversion of your message to bytes so that it can be moved from producer to consumer through the topic. Oh, great. We have the Kafka configuration ready. We have the producer ready. We have the consumer ready. We have the controller ready. What are we waiting for? Let's run it and let's see some exception will for sure happen. Why? Because we have not started the Zookeeper and the Kafka on the local system. So see, we get an exception. Broker, Bootstrap broker 9092, it is disconnected, cannot establish the connection. So how do you establish a connection? Go here and open the CMD. Here, I'm going to give you two commands. First is to run Zookeeper. Second is to run Kafka. Both will be given in the description below. For Zookeeper, this is the command that at the Windows, start the bat for Zookeeper server and get the properties from the config folder zookeeper.properties file. This will run the Zookeeper for us now. And after that, we should run one more command to run the Kafka. Now, this is the command to run the Kafka. So in the same folder, if you can go here, you can see in the bin folder, you have a Zookeeper start server.bat and also the Kafka server start.bat. So we are starting the Kafka server and we are also starting the Zookeeper server. So you can see this was the Zookeeper start server. Similarly, we need the Kafka server to be started and also get the properties for the server from this properties file. So the Kafka is running for us and it was able to find group has one member. So let's go and see. We were facing issue of connection error, could not be established. As soon as we started our application, Zookeeper and Kafka, it says successfully joined the group. And the group name is something which we have created, code decode group. It says successfully synced, adding the assigned partition to the topic. The topic name which we have created was code decode topic, right? What was the topic name? Code decode topic. Can you see that code decode topic here? And the partition is also added for that. This proves that our Kafka is now up and running. We have successfully started the Kafka server and the Zookeeper server. Now let's try and hit this controller with the REST API producer message. So it should be localhost 8080 because we are running on local. REST API producer message. REST API producer message, and the request parameter should be message. And that message should be congrats for first Kafka IMPL and hit. Congrats for the first Kafka IMPL. So our console successfully says the message is received. This message is received by the consumer who is going to listen to this topic. The topic I have already shown you in the previous console that the topic was ready. So what happened here was the producer was called with this particular REST API. You hit this REST API producer message with this message congrats. So this congrats message comes here. The producer is called to send this message to the topic. When you go to the producer send message to topic method, a Kafka template is used to send this message congrats for the first Kafka IAM implementation to code decode topic. In the console in the previous seconds, we have seen this topic was ready with one partition as 0th index. As soon as the topic has the message, it has a listener available. The listener was this consumer who was a Kafka listener for this topic in this code decode group that I've already shown in the console also. It listened to that particular received message and it prints the message is received. That is the received message is this. So this was the whole flow of this particular project. This project has already been uploaded in this particular Git location, GitHub, code decode 25 Kafka. SRC and everything is available here. You can take a reference from here while creating. If you find any issues, you can always refer to this particular public repository for which we have created for you. Now, with all these things in place, you have all these steps that you have done. You have created a Kafka dependency inform. You have created a controller. You have a producer, which is a service who is going to publish to the topic. You have a consumer who is going to listen to the topic. You have created some property changes. All of these property changes will be present here in application.properties file. In this main resources, you can find this application.yaml file. Then at going to the location, we have unzipped, where in the first step, we have unzipped Kafka. You have started the Zookeeper server and the Kafka server at this, and then you hit with this particular message. Now, what all we have done is we must have the Zookeeper for Kafka. Zookeeper performs many tasks for Kafka, but basically Zookeeper manages the Kafka cluster. By default, Kafka service started at 9092 and the Zookeeper started at 2181. That will be already, that I'll show in the next part where these configurations you can see that we have already seen a config folder. There all these configurations are there. Now group ID I have already told you, consumers in Kafka are divided into multiple groups and each group is identified uniquely by the group ID. The consumers belong to the same group, share the group ID. So the topic partitions are load balanced fairly between them. The consumers in a group that divides the partitions fairly among themselves as fairly as possible to establish that each partition is only consumed by single consumer from the group, so that they will not hit multiple consumers at a time to a single partition and bombard and heavily load that partition. Not to do that, each partition is going to be consumed by only single consumer from that single group. In Kafka template, I've already told you, that is used to send message. We have used Kafka template here. The send method is used. The first parameter is the topic name. Second is the message that you want to send to that topic. So all you need to do is the send method is called with the topic name and message. In order to prepare the message for transmission, the producer to the broker, we use serialization. I have already told you why we use serialization and deserialization, because we need to send data in the bytes in the topic. So you have to convert your string to bytes and then deserialize bytes to string so as to receive that from the topic. So that is why you need the string serializer that we have already created as a configuration part in the properties file. Now we have many more questions. How to change the Zookeeper default port number to 181, and how to change the Kafka port number, that is 9092. And what are the terminologies and architecture of Kafka? What is Zookeeper? Why is it actually used? How is cluster divided into multiple partitions, and many more things. And for that, we'll be meeting in the next video. Just let me know in the comment section if we can continue with this series. Thank you.
উবারে সিট বুকিং কি আরামের দিনকাল। আমাদের স্ট্রাগলের সময় না বাসের ভেতরে ঢোকা থেকে নিয়ে বেরোনো পর্যন্ত বোঝাই যেত না হাত আর পা ঠিক আছে কিনা। সিট ধরা চক্করে ঠেলা ঠেলি গুঁতো গুঁতি, ওরে বাবা, তার জন্যই তো এত সলিড হয়েছি জানো।
এখন চাই না আপনার ঠেলা ঠেলি গুতোগুতি।
স্ট্রাগলের দিন গেছে বেড়ো, এখন আরামের দিনকাল। সল্টলেক সেক্টর 5 এলে না, উঠিয়ে দিও।
Uber shuttle, no struggle.
Hi guys, welcome to Code Decode. Today in this video, we are going to cover some very important terminologies and architecture of components in Kafka. In the previous video, we have seen the implementation of Kafka by creating a Spring Boot application with producers and consumers and started two servers, that is a Zookeeper server and Kafka server, and we were able to send the data from producer to a topic, and our consumer was capable enough to fetch that data from the topic. With that implementation, we have seen a very basic demo of Kafka. Today, we will see the basic architecture of how this actually works internally. So we have created this producer, we have created this consumer, we have started a broker, which is a Kafka server. We have started a Zookeeper to handle these brokers, because these brokers are stateless. Somebody has to maintain these many brokers in a particular cluster. So the task of that was done by Zookeeper. That is why we have started two servers. Now with that in place, let's quickly see how this internally works, because we have seen the implementation. We should understand each and every terminology, how it internally works. So let's get started.
Please like, share and subscribe to support us, and we are setting a like target of 500 likes.
Let me first give you a very high overview of it. The main components of this Kafka architecture is a producer who produces the message, a consumer who pulls the message from the topic or the broker. At the larger overview, there is a big cluster with multiple brokers. In the previous implementation, we have seen just one broker. We have just started one server that for Kafka. But in real time, for the replication purpose and for the fault tolerance, we will have multiple brokers with replica of these partitions of a topic. So there will be multiple brokers in a cluster. So cluster will comprise of broker. Broker will have topic. Topic will have partitions, and partitions will have offset. So basically the architecture goes like this. There's a one big cluster. Cluster will have multiple brokers. Brokers will have topics. Topics will be divided into multiple partitions. Partitions will have multiple offsets, and each offset will contain single event or a message. So this is one-to-one mapping between an offset and a message. So one message will reside in one offset in a particular partition. There will be multiple partitions in a topic. There will be multiple topics in a broker. There will be multiple brokers in a cluster. And there will be one cluster managing all of these things with the help of Zookeeper. And Zookeeper's task is to manage these brokers. So producer will produce the message. The message will be consumed by the consumer. The broker will be the interface between the producer and the consumer. Broker will write the data to a particular disk space named as a namespace is named as topic. Topic is divided into multiple partitions. Suppose there are three partitions, partition 0, partition 1, partition 2. Each partition is divided into offset 0, 1, 2, 3, and so on. And each offset will have one single message. So here you will have message 1. When it is occupied, there will be message 2, which is produced by a producer, will be consumed by a consumer. So this is a very high level overview of the architecture of Kafka. So a topic is a bucket of message or events in case of Kafka, where services may place or read the message from. So basically, topic is a bucket of messages. Messages are organized and stored in topics. Topic is something similar to folder. So you can consider a topic similar to this folder code decode, and the messages are the files. But topics are divided into multiple subfolders or the partitions. So these subfolders can be partitioned, and inside these partitions you will have messages like you have files here. So you can consider a topic as a folder, the partitions as the subfolders, and the messages as the files in those subfolders. So topics have multiple producers, multiple subscribers, and messages can be read as many times as needed, unlike the traditional messaging queues like RabbitMQs, ActiveMQs. There, as soon as you read the message is deleted. This is not the case in Kafka because Kafka is multiple consumer. So even if you read a particular consumer reads the data, it should not delete it from the Kafka because another consumer might want to consume it. So don't delete it after you consume it. So the messages are not deleted in Kafka after consumption. Instead, you can define a particular time to live for those messages in Kafka. With that time to live, for that particular duration, message will be there in Kafka as long as that time doesn't expire. The Kafka topics are divided into partition. As already told, topics consider it as the folders. Partitions are subfolders. These partition contains the messages or the files in the subfolders in a particular sequence. Each message in the partition is assigned and identify a unique offset. A topic can have multiple partitions. So here, if you can see in this, you have multiple partitions. This allows multiple consumers to read from a topic in parallel way. With this partition, a consumer 1 is reading, and with this partition, consumer 2 is reading. With this particular partition, consumer 3 is reading. So this allows multiple consumers to parallelly use a topic as they are reading from a different partitions. Remember, a particular consumer can read only from a particular partition. One partition is to be read only and only by one consumer in a consumer group. If you have multiple groups, then it can be read simultaneously. We will see that in few seconds. In Kafka, replication is implemented at partition level. Now, I'll give you an example. What if this particular broker fails? So we have started a server in our local, right? What if that particular command prompt destroys, or what if the server crashes? What that particular broker is down? To prevent that situation, unlike what we have done to have a single broker, usually in real time, there are multiple brokers with the replication of data. So in a particular cluster, usually there are minimum of 3 brokers having the replication of data. So there will be one master or the lead broker who will read and write the data to a particular disk. Rest are the followers who will do the same which the leader is doing. So these broker is going to have the replication of these partitions. But in case of Kafka, the replication is always on the partition level. So always in Kafka, replication is implemented at partition level. The redundant unit of partition is called a replica. So this partition is a replica of this partition. So you have replicas on the partition level, not on the broker or the topic level, just on the partition level.
দাদা তাড়াতাড়ি চলো এবার আমাদের রাজ্যের পালা
খেয়েই যাচ্ছি অ্যাসিডিটি
কেউ ওকে জিরে দাও
আর জোয়ানো কালো নুন মিশিয়ে দিন
এসবের চেয়ে ভালো নতুন 3-in-1 এর ইনো খাওয়ান।
এতে আছে 3 এর শক্তি যা অ্যাসিডিটি থেকে দ্রুত মুক্তি দেয়। 3-in-1 এর ইনো তিনটেই এতে আছে।
Each partition usually has one or more replica over Kafka brokers in the cluster. These partitions will not reside in the same broker. Otherwise, if this replica resides in the same broker, if the broker dies, then even your replica will die and there will be no fault tolerance. That is why the brokers are used to have the replicas. Multiple brokers have the replicas, not on the same broker. Every replica has one server acting as a leader and the rest are the followers. So I can say this is the leader and this is the follower. The replica handles all read and write requests for a particular specific partition, and the followers replicate the leader. The leader is the one who writes to the disk, and the follower is going to replicate what leader is doing and will replicate the same read and write request to some another disk, so that if the leader dies, the producers and consumers can at least read and write the data to the replica of those, so that you will have the fault tolerance. So if the leader fails, one of the followers becomes the leader by default. This is the beauty of Kafka, and hence the fault tolerance is very beautifully managed in Kafka. Using the leaders and followers and having the multiple brokers having just nothing but the copy of the same data in a particular cluster. When producer publishes a message to the topic, it publishes to the leader, and leader appends the message to the offset. So what happens? How does producer writes to it? So producer write the data to the broker who is having the leader and not the follower. So producer always writes to the leader. The follower is going to replicate it, and leader appends that message to an offset. We will see how producer work internally in few minutes. Now, what is a Kafka cluster? I've already told you Kafka cluster comprises of broker, topic, partitions, and offsets. So Kafka cluster is a system that comprises of different brokers, the multiple topics, and their respective partitions. Now, what a producer and how producer produces or writes the data to the topic. So a producer sends the data to the topic within a cluster. Before producer sends any data, it has to request the cluster who is the leader. So currently producer is going to write the data to the particular disk to a particular topic. The cluster has multiple brokers. How will producer know where to write the data? So it has to first ask cluster, who is your leader? Now cluster will respond, broker 1 is the leader. This broker 1 is the information received by the producer. So now producer is going to write the data to this broker 1. In which particular partition, partition 0, partition 1 or partition 2 it has to write the data will be decided by the producer. Cluster is not going to respond it with the which particular partition it has to write. It has the task of producer to decide which partition, partition 1 or partition 2 or partition 3 or partition 4, it has to write the data to. So before a producer sends the data, it has to request cluster who is your leader. The metadata which is returned from the cluster contains the information which broker is the leader for which partition, and producer is always going to write to the leader partition. But now it is a task of producer to decide which partition it wants to write the data to. So there are 4 partitions, P1, P2, P3, P4. Which partition is going to be written by the producer is decided by a key. The producer attach a key to the message dictating which partition the message should go to. So I have decided that my message should go to partition 1. So the message, this 0th message will have a key appended which decides which partition. So it decides partition 1. So the data goes to partition 1. Now there are multiple offsets. So remember, data is always written in the partition in sequential manner in offset. So until unless the 0th offset of partition 1 is not filled, the first offset of partition 1 will not be filled. So producer uses the key to know which partition to write to, and by default the hash code is used of the key to calculate the partition. Now suppose my hash code becomes 1, the first partition of the topic will be used. If the hash code of the key is 3, then the third partition will be used to put my message to, and even the third partition will have the similar kind of offset implementation. A very important issue while doing such kind of hash code implementation of the key is setting the same key or the null key for all the messages. When this happens, all the keys hash code is same and they end up at the same partition in a topic, and hence unbalanced topic. So this topic is divided into 4 partitions, expecting that the producer will write to these all 4 partitions equally, so that topic is not unbalanced. Currently topic has 4 partitions, it is not unbalanced. If producer keep on writing all the data to the same partition, then your partition 2, 3, 4 remains unused, and hence the topic is unbalanced with partition 1 as all the overloaded. So remember to implement the hash of the key judicially, so that you don't overload a particular partition and not unbalance a particular topic. So this was all about producer, how producer writes it. So producer writes the data to a particular topic in a particular partition, in a particular offset, in a sequential manner. Which broker is the leader and which is the follower is given an information by the cluster, but which particular partition in the leader broker is to be written is decided by the producer using the hash code of a key which is appended in a particular message. With the decoding of that particular hash code, the partition is decided. Partitions are divided into multiple offsets. From that particular offset, the messages are written sequentially. How consumer consumes the data from the Kafka cluster? So consumer is the one who reads or consumes a message from the Kafka cluster. So this was our Kafka cluster. Consumer is sitting here. It reads the data from a cluster, from a particular broker, from a particular topic, from a particular partition, from a particular offset. Such a complicated task, right? So the beauty of Kafka is that each consumer knows exactly from where it has to consume the data to, and it is internally done by Kafka. You don't have to think about it. Now, it is a very complicated thing. I'm just going to give a very high level overview which is required for interviews. If you want to know deep about it, there's one book, a PDF I'm going to share. There you can read it, or you can just let me know. I'll just compile that in a video format for you. Let me know in the comment section. For this decision, consumers within a group automatically use a group coordinator. So basically, we have started a particular Kafka server, right? This broker is a Kafka server. So that Kafka server is going to assign the offset where the consumer has to read to. So there's a group coordinator from Kafka side and there's a consumer coordinator from the consumer side. And they both interact and decide which consumer will read from which particular partition offset in the topic in broker. This feature is already implemented in Kafka, therefore we don't have to worry about it. It's very complicated how these interacts. Let me know in the comment section if you want to know a very deep insight about it, but I don't think that is required from an interview perspective. The consumer reads the data from each partition in orderly manner. That means that the consumer is not supposed to read the data from offset 1 before reading from offset 0. So similarly, what I've told you in the producer will not write to the partition 3 before partition 0, 1 and 2. So it's a sequential manner in which the producer writes. Similar is with the consumer. Consumer also reads in the sequential manner from the partition. It reads from 0, 1, 2 and 3 rather than directly jumping to the fourth one. So it's a sequential manner. It is not supposed to read from the higher offset before reading the lower offset. Also, consumer can easily read data from the multiple brokers at the same time. There are type of consumers, basically two types, the lower level consumers and the high level consumers. Usually what we implement in our implementation also in the previous video, we have implemented a high level consumer with the consumer groups. This is created by assigning a group ID to a consumer. Here, if you can remember, we have given a group ID, code decode group. So we are saying that this particular consumer belongs to this particular group. There will be multiple consumers who can belong to same or the different group, which will be decided by this particular Kafka listeners annotations group ID attribute. If the group ID is same, those consumers belong to the same group. If they are different, they belong to different consumer groups. Giving the same group ID to another consumer means they will join the same group. Here we have already seen in the previous video that consumers are smart and brokers are dumb in case of Kafka, and it's opposite in case of ActiveMQs and RabbitMQs. Why we have said that is because it's a task of consumers to pull the message from the topic. Here, if we can say brokers are dumb, they just sit idle and will say, okay, just come to me when you need the data, I'll give it to you. It's a task of consumer to pull the data from the broker from the topic. So these are smart consumers and dumb brokers. They are lazy. They just sit idle. The task of consumer is to pull the data from the topic. So consumers pull the top messages from the topic partition. Messages are never pushed to consumers like as we used to do in the ActiveMQs, RabbitMQs. Consumers will ask for the message when consumer is ready to handle the message. The consumer will never overload themselves with lots of data and does not lose data since all messages are being queued up in the Kafka. If consumer is behind during the message processing,
Okay. Yeah.
गरम लैपटॉप कब तक चलाओगे? आ गया है नया लैपटॉप लेने का बेस्ट मौका फ्लिपकार्ट के बिग दिवाली सेल के साथ.
So suppose there's some issue with the consumer and it is behind processing, what it will do is it can reset its offset value and reread from the previous offset. So it has an offset to reset the offset value while reading from and read again from the previous offset. So that is why it says consumers are smart consumers. We have seen producers, we have seen consumers. It's time for the brokers and partitions. The broker, a Kafka server, broker, a Kafka node, all refers to the same concept. In our case, we have downloaded a Kafka and we have run a particular command, that is Kafka server start.sh script. With this particular script, we have started our node, broker or server. So I can say that only one broker is what we have started initially. A broker is a bridge between producer and a consumer. If producer wishes to write data to the cluster, it sends it to the Kafka server. So the task of server is to get the data and write it to a particular disk space. A Kafka broker allows consumer to fetch the message from the topic, partition and offset. So the task of broker is to get the data from the server and write it to the disk space and allow the consumers to fetch it from the disk space. All of these brokers lie in the cluster. To maintain the load balance, cluster typically consists of multiple brokers. To not only just the load balance, but also to prevent the failures, we have multiple brokers in our clusters. You can start a single broker using the script that we have shown in the previous video. But running a single script is possible, but it does not give all the benefits that Kafka give in a cluster. For example, of data replication and failure tolerance. So if you have just single broker, there is no other broker to replicate your partition, and hence in case this particular broker dies, nobody is going to take over this particular broker and your whole system will crash. So that is why it's always said that you should have a cluster having multiple brokers having the replication of partitions, so that if the leader dies, followers can become a leader. That was all about brokers. Now partition, we have seen this is a partition. This partition, there is one partition which is the leader partition. There is all the others in the other brokers are the follower partitions. And always replication is done in the partition level. Partitions are divided into offsets. Always is written and read in the sequential manner. Let's go ahead with the Zookeeper. Now in the previous video, we have not just started a Kafka server. We have also started a Zookeeper server. And why did we do that? The reason why we also implemented and started the Zookeeper is for the managing and coordinating between multiple Kafka brokers. So if you can see, we have a cluster, we have multiple brokers. Brokers will have the replication of data so that to load balancer have the fault tolerance. Now these brokers are stateless. So to maintain the state and coordinate between multiple brokers, if the broker dies, make the follower the leader, all these tasks will be done by somebody has to do that. That's not a task of producer and consumer. Producer is just to produce, consumer is just to consume. Who will manage these brokers? When one dies, another has to become the leader. That will be done by Zookeeper. So the purpose of managing and coordinating the Kafka brokers, we have used Zookeeper. So Zookeeper stores the information about the cluster. Basically, cluster contains the brokers, and hence the Zookeeper manages the information about brokers. It manages broker by maintaining the list of them. Management of broker is performed by Zookeeper. There will be multiple Zookeepers in the cluster. Now, we know that brokers are stateless, and hence to maintain the cluster state, we use Zookeeper. Zookeeper is also responsible for choosing the leader for the partition. Now, in the previous slide, we have seen that there is a leader and the rest of them are the followers. Who will be the leader will be decided by the Zookeeper. And that knowledge about who will be the leader is given to the producer by the cluster. And who decides the leader? That is the Zookeeper. Also, it used to notify the producer and consumer about the presence of any new broker, or if this particular broker fails, to whom the producer can write to the new broker, and whom the new broker the consumer can consume from will be decided by the Zookeeper only. So if the leader dies, if there are multiple followers, which of those followers will become a leader, and who will tell the producer, sorry, your old leader dies, now you write to the new follower, and which is the new leader is decided by the Zookeeper. As soon as Zookeeper sends the notification regarding the failure of a broker, then the producer and consumer take the decision, okay, stop sending the data to the broken broker and start sending the data to the new leader decided by the Zookeeper. It also notifies consumer the offset value. So we have seen this is a very hectic task, how consumer reads it, but who decides from where it has to read the data again in the consumer is decided by the Zookeeper. Now Zookeeper is designed to operate with the odd number of Kafka, so that is why it's always said at least have 3 brokers when you design a particular cluster in Kafka. The zookeeper has a leader server that handles all writes, and there is a follower who handles all reads. However, we do not indirectly interact with zookeeper, but we interact with the zookeeper via brokers. No Kafka server can run without zookeeper. So in the previous video also, before starting the Kafka, we have started zookeeper. So it's mandatory to run zookeeper before Kafka server. If you do in the opposite direction, you will not be able to implement it properly. That was all about Kafka. Now we have Kafka streams. If you want to know about Kafka streams, let me know in the comment section. I'll create another video. And also I can create one separate video for you, which is only from the interview perspective. These 3 videos were the tutorial ones. If you want to know just about the interview questions, let me know in the comment section. I'll create a separate video covering only and only the interviewed questions. Thank you.
AJ, what's up?
I don't know how to explain this, Kavya. It's a thrill.
Thrill.
And it goes on and on and on. It's a turbocharged, incredible feeling.
Hey guys, welcome to Code Decode. In this video, we are going to look into the distributed transaction management and the ways to manage this distributed transaction, be it synchronous or asynchronous ways. So from synchronous, it's 2PC, 3PC, and asynchronous we have already covered, that is Saga design pattern. Now let's start and see the 2PC first. Now to start with, let's start what is a transaction. So a transaction is a series of actions that must be executed. If even one of the operation fails, the complete transaction must be rolled back. A transaction is something which follows the asset properties. So I'll give you one example. You are working with an e-commerce website. So you place an order. What happens first is the inventory is reduced so that another person should not see that particular product if the inventory was only one and you have taken it. So the first thing that has to be done after the placing of an order is to reduce an inventory. Then it should ask you for the payment, and if payment is successful, your order is placed successfully. Now this is a series of event and hence it is a transaction. Place an order, reduce an inventory, make the payment. When successful, make the order successful. So basically it should have a asset property being followed upon. Be it monolithic, be it microservice, asset properties has to be followed. So what is an asset property? It says A for atomicity. That is, when we place an order for a particular product, the order service deducts the order quantity from inventory service and the payment service processes your payment. But atomicity makes sure that if the inventory is successfully removed but your payment is failed, that means your order is not placed successfully, then it is unfair to the other people to not to be able to place the order for that particular product which you did not have made the payment for. Hence, if you make the payment, then only the inventory should be reduced. If the payment is failed, order is failed, and hence inventory should again jump back to the previous state. So it's atomic in nature. It happens completely or it doesn't happen at all. Next is consistency. It says that your inventory should always remain accurate and consistent with the actual stock. Now suppose I have only one inventory for a particular product. Now what happens if you place an order? That is reduced to 0. In that case, your order will be accepted and you can make the payment and your order is successful. But what if you make for 2 quantity, but you have only 1? So the inventory becomes negative. So this is an inconsistent state because it does not make sure that you have an accurate and consistent stock, because -1 is not a consistent state of the system. So it makes sure that the inventory does not drop to the negative quantity. And hence in that particular scenario, you have to roll back the whole transaction because you have ordered the number of quantity which is more than the actual stock. So in that case, the transaction is rolled back, making sure that your system is consistent. That means you have not taken an order which is expecting you to have the quantity of product which is more than your actual stock in the inventory. So that makes sure that your system is consistent. The next is isolation. So when you have multiple consumers placing an order simultaneously, so suppose A is placing an order through order service, customer B is placing an order for the order service. Now in isolation makes sure that A does not see the immediate state of B and B does not see what A is doing in the system. So there should be no interference for the concurrent transactions. So A is doing something, B is doing something, A should not be able to see what B has done. B should not see what A has done, but at the end, both tasks should be done. So isolation is nobody interferes in anybody's task. Durability says that after successful deduction of inventory and payment is processed successfully, the data is persisted in database. That means if I have one quantity of a product and if my order is placed successfully, my payment is also successful, the inventory should be made as 0 as the order is successful and payment is also done. If in that particular case, once the payment is also successful, inventory is also reduced to 0 and order is also successful, if this time after all these things are done, if the system crashes and if it comes back again to life, then it should not show any inventory for the previous product. It should be 0. So after a successful completion of a transaction, the data should be persisted properly in the database or your hard disk. It should not roll back in any case. So in the case of system failure or the restart, the committed state is recovered from the durable storage, be it database or be it hard disk, and the system resumes with the consistent and correct data. That means you have a durable data. So these were 4 asset properties. Now next is how the transactions are different in monolithic and microservices. So in traditional monolithic, all this happens like placing an order, reducing an inventory, making the payment, and placing an order as successful. Everything happens in one single database. So the transaction boundary starts in your business layer or the service layer and can be committed and rolled back based on the outcome of each step. So it's not a problem. You can just put an transactional annotation and everything can happen in that particular method only, making all these things as a child transactions. If you don't understand this, you can just have a look at the transaction management, the video that we have created for the Spring Boot. Now, if this was a monolithic part, it would have been very easy. But when it comes to microservices, you have a single responsibility principle being followed. And what the single responsibility principle says? It says that each particular service should have its own single responsibility. So each microservice has its own DB and another service should not interact with the DB of that particular microservice directly. So these transactions becomes distributed. Why? Because now each of them are going to have their own databases. So now this is order DB, then this is inventory DB, and this is going to be the payment details DB. For a particular client, there might be multiple payments and they can have multiple payment methods in which you can store in your tables also. So that can be there in this particular DB. Now you as a client adds the product and goes to buy it on a particular website. Now the order is created. The item stock has to be reduced by 1 since you are buying that product and the payment is successful. In the monolithic architecture, all are going to have single DB. And if any of this step fails, so payment fails, the inventory should go up again by the amount and the order should be failing. So all this happens in a particular same class, business layer or the method, and hence any step fails, the transaction is completely rolled back. But this is not the case with microservice architecture. For microservice architecture, each step takes place in an individual microservice with its specific database associated with it. So now order will be processed in order service, stocks will be checked in inventory service, and payment will be done with the payment microservice. Now, since each step runs in a different microservice, maintaining asset properties is very difficult and complicated. And hence comes the distributed transaction. Now, what is distributed transaction? A transaction that is coming across the multiple applications or the microservices becomes a distributed transactions, and maintaining the asset properties across these microservices is very difficult task. So basically there are 2 ways to handle it. The first one is synchronous and second one is asynchronous ways. So synchronous transaction management can be divided into 2-phase commit and 3-phase commit, while asynchronous we have already seen, that is Saga design pattern. Hey guys, recently we have launched a course covering an end-to-end full stack application using Angular as front end and microservices and Spring Boot as the back end. Also, we have used Cloud to deploy this application, and we have used CI/CD, that is Jenkins and Argo CD, for continuous integration and continuous deployment. technologies that we have used is REST, RESTful web services, Spring Boot and microservices for backend, Angular for frontend. GitHub we have used for version control system. Also, to make the code unit testable, we have used JUnits. We have used Sonar for code quality checks. Also, for containerization, we have used Docker and Kubernetes. And to deploy this whole application, we have used AWS and multiple services from AWS. Also, we have used SQL as well as NoSQL, that is MongoDB and SQL. On AWS, since for the SQL we have RDS, we have used those services, and Jenkins and Argo CD for CI/CD pipeline. Also, this is an architecture of the application that we have created where the front end is Angular and the back end is microservices. We have used ALB load balancers, Ingress for routing and load balancing. And we have used SQL and MongoDB for SQL and NoSQL DB management with Eureka Server and all those microservices counterparts. Now, this is the CI/CD pipeline. This is the CI/CD flowchart for the application that we have created on local. So this is something, a flow when you create an application in local, push it to GitHub, create a Jenkins pipeline and do the CI/CD using Jenkins and Argo CD. And at the end, deploy the whole code at AWS EKS. Complete description of this course is covered in a very separate video. The link for that video is also given in the description bar below. And also the link to purchase that course from Udemy is also in the description bar below. So please go and check the description for all these links. So let's first see the two-phase commit, which is a synchronous way of distributed transaction management. The two-phase commit is a protocol. So it's just a protocol, the way of doing thing. It's not the code implementation. So it's a protocol to handle the distributed transaction using the two stages. As the name says, two-phase. The first phase is prepare phase and the second phase is commit phase. So let's see the phases here. So this is a client. Client says, I want to place an order. So now what all things will happen in the backend? Order service will come into picture, inventory service comes into picture, payment service comes into picture, and at the end, so client will be responded back as order is successful or order has failed. So these are two possibilities. Now it seems very simple that client says, I want to place an order. The response comes order placed successfully or order failed. But behind there are multiple things happening at multiple microservices. And at the backend, what happens is the one of the service, that is order service, becomes the transaction coordinator in two-phase commit. What happens is order service says we have a request to place an order. So order service acts as a coordinator. So order service says prepare to payment service and inventory service. What payment and inventory service do? They check whether they can fulfill their part of transaction. Means they check whether inventory is there or not. And by reducing it by the required quantity doesn't make the system inconsistent or in negative inventory source. So every service does its own task and see whether this is doable or non-doable. So payment service says, oh, I do not have any payment details. I cannot take the payment. So in that case, it will say, no, we are not prepared. So order service sends a prepare message to all the participants. So once the prepare message is sent and all the microservice says, yes, they are ready. By reducing the inventory, we are still the consistent state and I have proper payment details with me. We are ready to place an order. So all the participants vote with yes or no. If everybody says yes, then coordinator is good and they say commit. But if any of the participants say no, that means either you do not have the payment details or the inventory after reducing the required quantity becomes negative and the system becomes inconsistent. In that case, if any of the microservice says no, then the coordinator says rollback. So this is a second stage. First stage is prepare. The second phase is commit or rollback. So that is a decision phase. So if all microservice says yes, then only the coordinator says commit. If any of the microservice say no, it sends the abort message to all the participants. And in this phase, the actual changes happens. So you might have kept your inventory reduced by the required quantity, but it is still not committed to database until the commit phase comes. So in the first phase, the prepare phase, you do everything, but you do not commit anything to the database or you do not make any payment request to client. Now, once you have the commit phase. That means the payment service knows that yes, you have the inventory. Inventory service knows that yes, at least if I reduce the inventory, we have payment details with us, we can ask for the payment from the client. So when everybody knows that yes, everyone is ready, then the coordinator sends the commit message to payment service and inventory service. So as soon as the commit comes, the inventory is actually reduced in the database and the payment request is sent to the client. Once the inventory is reduced successfully and the payment service has also taken the payment from the client successfully, then only the coordinator sends to the client that yes, your order placed successfully. Now even this can die in acknowledgement phase also. So if the inventory is for any case not reducible or makes the system inconsistent, or the inventory service dies or something wrong happens with the network, then the acknowledgement doesn't come to the coordinator. Also in the case of payment service, if the payment fails, the acknowledgement is not sent to the coordinator. In that case also, the abort or the rollback command is given by the coordinator. So after successful completion, each microservice sends an acknowledgement to order service. If all acknowledgements are received, order service says that okay, my transaction is complete, client, your order is successful. But if anybody's acknowledgement is missing, then there must be some execution encountered issue. Like for example, any of the service might have crashed or the timeout has happened. In that case also, order service sends the failure notice to client and ask everybody to roll back. Now you can see some very clear drawbacks of this 2PC. The first is a coordination overhead. There's a multiple rounds of communication and synchronization can introduce overhead, and hence complete performance and scalability is reduced in this particular case. So everybody is blocked. What happens is when order service says, are you ready? So inventory service tries to reduce and see whether it is capable enough to reduce the quantity or not. Also by that time, payment service, even though it has all the payment details with us, will not be able to take the payment from the client because it does not know whether inventory service is proper inventory or not. So this is a complete synchronous communication. Also, there is a communication overhead until the coordinator doesn't sense, okay, now we all are ready. Now you can commit. Till then, everybody is blocked. They have done their local part. They have reduced the inventory in local. They have checked and validated the payments, everything. But they cannot ask for payment from the client and they cannot reduce the inventory from the database until the coordinator doesn't say that yes, everything is perfectly fine. So there is a coordination overhead in this particular 2PC. Also, there is single point of failure. If the coordinator, that is order service, dies, what happens? Nobody gets the commit message. No, everybody is left in dilemma whether they have to commit or they have to roll back, whether other microservices are up or running or not. So this is a case of single point failure. If coordinator does not sense the commit or rollback, everybody is in inconsistent state. Also, it's blocking. So the synchronous has a blocking issue. During the 2PC execution, till inventory service does not make sure that yes, the quantity is there, payment cannot be taken. So this leads to performance issue. And since everybody has to wait, the decision is completely blocking. Now, there is also a case which is handled by 3PC. That is blocking during coordinator failure. So if coordinator fails, you know that there is an issue. Nobody knows what to do next. They have to commit or they have to roll back. So even if the coordinator sends a commit message, but it does not reach to any of the microservice, this leads to the participants being in uncertain condition. So in this case, participant, what they do is they have some timeouts. So they wait for like 2 minutes. If the coordinator does not send you to commit, they understood that the coordinator might have died. In that particular case, in the certain time frame, they roll back. Hence, these particular issues are sometimes, many a times, resolved by 3PC also. In the next video, we'll be seeing some 3PC scenarios. But there are some failure scenarios for 2PC. What are those? The failure scenario includes a participant failed during a prepare phase. So a participant might have sent, yes, I'm ready. So inventory service might have sent, yes, I have inventory. But in the meanwhile, inventory service got crashed. So coordinator did not receive the yes from the inventory service, even though you have the inventory. Since it does not get any inventory response from the inventory service, it thought, oh, inventory is not there, or inventory service might have down. So this is a participant failure, and this system might fail at that particular time. Also, participant failure occurs during the commit phase. So what happens is inventory service says, yes, I have inventory, go ahead. Payment service says, yes, I have valid payment details, go ahead. Now, during the commit phase, the inventory was not able to commit and reduce in the database. So it knows that, yes, it has the inventory, but it is not able to reduce the inventory from DB because in the commit phase, inventory service got down. In that case, acknowledgement is not sent to the coordinator. So coordinator will assume, oh, it was able to reduce, but it is actually not able to reduce currently because of some network or crash failures. In that case, it will again say roll back, sorry. Even though we have everything, we cannot proceed with your order. The third is coordinator failure while sending the commit message. So these were the cases when participant failed during prepare and commit phase. Now, third is the case where coordinator itself failed. Now, payment and inventory service are sitting there idle thinking what to do. There is a commit or there is a rollback. So what they do is they wait for some time, for 2 minutes says, and then they say rollback. We are not able to handle your orders currently because my order service is down. Also, fourth case can be the network issue. So there can be loss or delays in the communication. So what happens is coordinator says, okay, commit. But due to some delays or the network issues, this reaches after 2 minutes. And 2 minutes was the timeout for payment service and inventory service. So they both says, oh, coordinator is crashed. Even though it is not crashed, there was a network delay. Still they think that they might have died. So what they do is, even though they were asked to commit, they would have rolled back. So this is also where the 2PC might go down. Timeout thus seems to be very critical and crucial in two-phase commit. Because participants also wait for the coordinator, coordinator also waits for the participants. And to prevent the indefinite blocking and the bad user experience where your timer just keeps on running, order is getting placed, we are checking, order is getting placed, we are checking. To prevent such bad experience to users and unresponsiveness of the application, we always used to have the timeouts, which is very critical in two-phase commit. Now a question can be asked, when to choose synchronous or the two-phase commit. So you will choose the 2PC, that is a synchronous way of handling the distributed transactions in the scenarios where there is a very business criticality. So where the success and failures is a significant impact on business. So what it does is, until unless all the participants does not give you the response is not sent back to the client. So client waits till that particular time. So that is synchronous. So when the business is that much critical, for example, in a financial transaction. So it says that there is a financial transaction happening. If it is completed, then only client should say that yes, the financial transaction is completed. So that the data always remains accurate. You cannot be okay with the consistency getting reduced. So whenever you need a great data consistency in this distributed system and you need a strong consistency guarantee with multiple participants, then 2PC or the synchronous communication is good. So if you want to know more about the 3PC, which is also a better version of 2PC, let us know in the comment section. We will create another video for the same. Thank you. Hey guys, welcome to Code Decode. In this video, we will be looking into the 3-phase commit. So in the previous video, we have seen 2-phase commit. Now, if 2PC was there, why was 3PC introduced? What was the need of 3 phases now? I'll give you a scenario and you will clearly see that why 3PC was introduced. So this was the 2PC, right? So here was the order service, the payment service and the inventory service. The client comes, sends the request for order service to place an order. Internally, the request goes to payment service and inventory service to check the payment, take the payment, to check the inventory, reduce the inventory by the required quantity. Now, the phases were the voting phase and the commit phase. Only 2 phases. The first one was the voting phase and second one was the commit phase. Now, I'll give you one scenario, okay? During the voting phase, what happens is order service says, are you all ready to commit? The payment service checks its own payment details and says, I have payment details with me.